The United States Marines have new vessels the world doesn't know about. Hidden away from prying eyes, the U.S. Marines are deploying powerful new combat boats, each worth a mind-blowing $500 million. Built for speed, stealth, and unmatched firepower, these high-tech vessels are designed for secretive operations in the most challenging waters. But what makes these boats so special, and why are they kept under wraps? Let's explore the capabilities of the $5 million combat vessels that the U.S. Marines have been hiding. For years, attention has focused on the Navy's mighty aircraft carriers, highlighting their power and influence. While this is certainly true, combat boats often go unnoticed despite their essential role in naval operations. Well, just like the USS Gerald aircraft carrier is the most powerful in the world, we would be unveiling some powerful combat boats that the U.S. has deployed in secret. Beginning with the Combatant Craft Medium, or Mark I CCM, often used by Navy SEALs and other special operations forces, it is a U.S. Navy patrol boat made for the Navy's Special Warfare Command. Built by Vigor Industrial, this versatile boat can handle many missions. The CCM is highly secretive, designed for stealth and speed, and used for secret missions, including reconnaissance, rapid insertion and extraction, and special operations in hostile or denied areas. It is also designed to support special operations by providing small-caliber gunfire, carrying forces into and out of mission areas, performing coastal patrols, stopping and searching other vessels, and carrying out counterterrorism and reconnaissance. The CCM also assists with training allies in defense tactics. The Combatant Craft Medium was first planned as a replacement for the retired Mark V Special Operations craft, but the initial proposal was canceled in 2010. Later, the U.S. Navy requested a new design that could be transported by a C-17 aircraft instead of the smaller C-130, which had carried older RH-HIBs used by naval special warfare. Designed by Michael Peters Yacht Design, the CCM grew from Oregon Iron Works' earlier Alligator and Sealing models, initially developed with help from Israel's Defense Forces. In 2011, Oregon Iron Works and United States Marine Inc. received contracts to adapt their designs. Oregon Iron Works was ultimately chosen in 2014 to build 35 CCMs over 7 years under a $400 million contract with U.S. Special Operations Command. Shortly after, Oregon Iron Works joined with Vigor Industrial to help manage production, with Leidos handling electronics. The first CCMs, arriving in 2015, offered a low-profile design with longer range, improved stability in rough seas, and better protection for crews than the older RH-HIBs. The boats also came with advanced equipment, like remote weapon stations, tracking systems, GPS, and tactical radios. While each boat is numbered, they aren't given names and are operated by SWCC boat teams. In May 2023, Norway's Naval Special Operations Command received U.S. approval to buy 2 CCMs, expected for delivery in 2025. Another boat rumored to be part of the U.S. Special Operations Fleet is the Stiletto, also known as the M80, an experimental vessel known for its innovative hull design that allows for stealth and minimal radar detection. Although not officially classified as secret, its capabilities and operations are closely guarded. Also, these boats allow special forces to operate covertly, often in high-risk, sensitive areas where stealth and minimal detection are crucial. The M80 Stiletto is a fast U.S. Navy vessel designed to operate close to shore. At 88 feet long, its unique M-hull shape offers a stable yet quick platform for carrying surveillance equipment, weapons, or special ops teams. This hull design helps it stay steady even at high speeds or in rough waters, without needing extra stabilizers. With a shallow draft, the Stiletto can travel in shallow coastal areas, rivers, and even beach landings. Its sleek front design makes it harder to spot on radar. It's powered by 4 Caterpillar engines, hitting speeds over 60 knots and covering up to 500 nautical miles fully loaded. Jet drives can also be added for operations in shallow waters and beach landings. A rear ramp allows for launching and retrieving small boats or underwater vehicles, while the top deck can launch drones. Weighing 45 tons, it's light enough to be lifted onto a cargo ship, yet can carry a hefty 20-ton payload. Built with strong, lightweight carbon fiber materials, the Stiletto costs about $6 to $10 million per craft, making it the largest U.S. naval ship using these advanced materials. Moving on to the most recent U.S. combat boat, the Mark VI patrol boat. Designed for the U.S. Navy, it was introduced in the mid-2010s to provide enhanced coastal and riverine defense capabilities. The Mark VI is a fast, agile boat with a range of about 600 nautical miles and a top speed exceeding 35 knots. It's equipped with advanced weapon systems, including remote-controlled machine guns and missile launchers, and offers superior surveillance capabilities. This patrol boat is used by the U.S. Navy to operate in rivers and coastal waters. The first two Mark VI boats were sent to Coastal Riverine Group 2 in September 2015. In April 2016, 2 boats were sent to Bahrain, making Coastal Riverine Squadron 2 the first to use them in the Persian Gulf under Task Force 56, replacing the older Riverine command boats. In 2016, 2 more boats joined Coastal Riverine Group 1 and were deployed to Guam in 2017. Another boat went to Bahrain in 2018 to replace a prototype craft that was then returned to the U.S. and put into storage. A third boat also went to Guam, completing the initial deployments. Rotating crews from the Navy's Coastal Riverine Force handled these forward-deployed boats. By 2018, all 12 boats had been delivered, completing the Navy's order, although several other countries are interested in possibly buying the Mark VI boats for their own use. What led to the creation of these sophisticated combat vessels? The Mark VI patrol boat, built by Safe Boats International, marks a shift in the Navy's focus from deep water battles to coastal and shallow water operations. Replacing the older riverine command boats, it is bigger, tougher, and packed with modern weapons, advanced communication, and surveillance tech. It's not a substitute for the Mark V Special Operations craft used by Special Warfare combatant crewmen from 1998 to 2012. This patrol boat handles a range of missions, from patrolling shallow waters and conducting search and seizure operations to escorting important cargo in foreign ports and supporting special forces. Safe Boats delivered the first of 12 Mark VI vessels in 2014, with the first 2 officially joining Coastal Riverine Group 2 on September 8, 2015. By 2018, 3 Mark VI were operating in the Persian Gulf with the U.S. Fifth Fleet. Let's get into the details of what exactly they look like. The Mark VI patrol boat is an 85-foot powerhouse, much larger than earlier Navy patrol boats, with room for a crew of 10 and space for 8 additional personnel. Inside, it's built for comfort and endurance, featuring shock-absorbing seats, noise-reduced berthing, and a galley, allowing the crew to handle rough seas without excessive fatigue or risk. Its advanced tech suite offers real-time command, communication, surveillance, and intelligence, enhancing situational awareness and adaptability for various missions, with screens throughout for crew updates. Standard armaments include 2 remote-controlled 25mm guns and 6 50 caliber machine guns, plus mounts for M250, M134, and MK-19 grenade launchers. The boat also features the MK-50 gun weapon system for remote operation below deck and can be fitted with BGM-176B Griffin missiles. Lightweight armor protects critical areas like crew spaces, engines, and fuel tanks. Powered by 2 MTU diesel engines, this patrol boat can reach over 35 knots, 40 miles per hour, and cover 600 nautical miles. The flexible aft cabin can hold Navy SEALs or medical supplies, while the rear deck allows for launching small boats, drones, and underwater vehicles. Its height-adjustable mast lets it fit into amphibious ship well decks, enabling easy deployment from various Navy ships. Each Mark VI costs $15 million. Amongst the Marine combat boats are littoral combat ships, or LCS. The Freedom class is one of 2 ship types in the U.S. Navy's littoral combat ship program, designed for operations in coastal waters. Created by Lockheed Martin and Fincantieri's subsidiary Marinette Marine, it competed against the Independence-class ship by General Dynamics and Austal to build a fleet of small, versatile warships. The Freedom-class ship is a semi-planing steel monohull with an aluminum superstructure. It's 377 feet long, weighs 3,500 metric tons, and can reach speeds of 47 knots. Designed for flexibility, it has a modular frame for quickly swapping mission modules, a helicopter deck with launch and recovery capabilities, and launch areas for boats at the stern and side. A Trigon system moves helicopters in and out of the hangar, while a stern ramp and a starboard door allow launching of mission equipment. Inside, a 3-axis crane helps handle modules or cargo. However, the ship has had electrical issues. The front deck holds a modular weapon zone for either a 57mm gun or a missile launcher, with a rolling airframe missile launcher above the hangar for defense and .50 caliber guns on top. The Fleet-class unmanned surface vessel can operate from this ship type. The ship typically has a core crew of 40, plus mission and aviation teams, totaling around 75. Automation allows a smaller crew, cutting costs, though the workload can be tough. 2 ship crews rotate on 4-month deployments. 4 diesel generators provide 3 megawatts of power, covering the ship's needs. While fuel costs are estimated to be only 8% to 18% of total operating costs, there's debate over fuel efficiency compared to the Independence class. In 2012, a cybersecurity check highlighted weaknesses in the Freedom class's computing system, which manages the whole ship. Critics argue that both the Freedom and Independence classes have lower survivability than the frigates they're meant to replace. However, Lockheed says the Freedom class hulls are stronger due to advanced steel, making them more resilient than earlier frigates. Milwaukee was the first ship in the Freedom class to use advanced cavitation performance water jets, specifically the Rolls-Royce Axial Flow Waterjet MEMS K1. These innovative jets create partial vacuums in water thanks to a better blade design. While they don't boost the ship's top speed, they improve fuel efficiency by 10% and reduce noise and vibrations. This means lower life cycle costs, easier maintenance, and potentially better performance at slower speeds. In 2014, the Navy decided to add these water jets to all future Freedom-class ships. The early Freedom and Independence-class ships were delivered before their designs were fully developed, allowing for improvements to be made in later models. Many enhancements for the Freedom class stemmed from issues encountered during Freedom's first deployment, such as power outages, corroded equipment, and a malfunctioning air compressor. To improve reliability, the anchor winch, hydraulic unit, and mooring capstan were replaced with a single electric chain winch on the main deck, and a lighter towing chain was introduced to keep water out of the anchor windlass room. To combat corrosion, the impressed current cathodic protection system was upgraded by adding protections to the water jet inlet tunnel. Changes began with LCS-3, which saw a longer stern transom and additional buoyancy tanks to enhance stability and service weight. Additionally, LCS-5 featured a simpler gas turbine electric start system to help cut costs and reduce the ship's overall weight. Starting with LCS-17, Freedom-class ships will be outfitted with the advanced TRS-4D naval radar. This AESA radar, made by Airbus Defence and Space, is similar to the one used in German Fohn 25-class frigates, but will feature a rotating design, marking the first use of an AESA rotating radar on a U.S. Navy ship. The TRS-4D combines mechanical and electronic scanning for 3D capabilities, making it more sensitive to detect smaller targets with greater accuracy and faster tracking speeds. The Independence class is the second class of littoral combat ship. The whole design originated from a project by Austal aimed at creating a fast ship that could cruise at 40 knots. This design eventually became the high-speed trimaran ferry HSC Benchijigwa Express. General Dynamics and Austal then proposed the Independence class as a contender in the Navy's plan to create a fleet of smaller, agile warships for operations near the shore. Initially, only 2 ships were approved to compete with Lockheed Martin's Freedom-class design. Although the plan was to build only the winning class, in 2010, the Navy decided to order up to 10 more ships from each class, making a total of 12 ships per class. In March 2016, they announced plans to add 2 more ships, increasing the total order to 13 for each class. In early September 2016, it was revealed that the first 4 ships of the LCS program would serve as test ships instead of joining the fleet. This group includes the lead ships Independence and Coronado. As of May 2019, 9 ships had been commissioned. In February 2020, the Navy announced plans to retire the first 4 LCS ships. On June 20, 2020, it was confirmed that all 4 would be taken out of service in March 2021 and placed in inactive reserve because upgrading them to match the newer ships would be too costly. The Independence-class design started at Austal as a plan for a fast cruise ship. The main goals were to achieve speed, stability, and passenger comfort. The team discovered that a trimaran hull provided better comfort and stability compared to catamarans and monohulls. This idea eventually led to the creation of Austal's high-speed ferry, the HSC Benchijigwa Express. These ships are impressive, measuring 418 feet long, with a width of 104 feet and a draft of nearly 13 feet. Typically, the crew consists of 40 sailors, but this number can grow depending on the ship's mission. The living quarters with bunks are located beneath the bridge, and instead of traditional steering wheels, the helm is operated using joysticks. Thanks to the trimaran hull, these ships can still reach impressive speeds of about 50 knots and travel a long distance of 10,000 nautical miles. Austal claims that their design is more fuel efficient, using about a third less fuel than the competing Freedom class. However, the Congressional Budget Office noted that fuel costs would only make up 18% or less of the total lifetime cost for the Freedom class. One major issue with the Independence class is the lack of bridge wings, which has been identified as a significant problem in the entire LCS program. Retrofitting these wings onto existing ships will be necessary. Additionally, the lightweight aluminum used in the Independence class ships makes them more susceptible to damage compared to the Freedom class vessels. The first ships of both LCS classes set sail before their designs were fully polished, paving the way for exciting upgrades in future vessels. The Navy is enhancing the Independence class with bridge wings for improved safety and replacing the 17-foot rigid hull inflatable boat with a beefier 23-foot model. To combat corrosion, a new protection system will be installed, ensuring these ships can brave the elements. Like their Freedom class counterparts, Independence vessels will utilize axial flow water jets, which push water parallel to the impeller shaft, boosting efficiency and cutting down on maintenance. What's truly innovative about the Independence class LCS is its versatility. These ships can switch roles by changing mission packages, each equipped with specialized gear like weapon systems and sensors. The Navy has a range of mission modules lined up, focusing on anti-submarine warfare, mine countermeasures, surface warfare, and special operations. The plan is for the mine countermeasures and surface warfare modules to be ready by 2014 and the anti-submarine warfare module by 2016. The Independence class is armed for self-defense and command, but what sets it apart is its ability to utilize tailored mission modules rather than fixed weapons. These modules can include everything from manned aircraft and drones to off-board sensors and specialized teams. With interior space larger than some destroyers, these ships serve as impressive platforms for rapid transport and maneuvering. They are equipped with the advanced Raytheon CRAM missile defense system, which cleverly combines the sensors of the Phalanx 1B weapon system with an 11 missile launcher. They are outfitted with cutting-edge radar and communication systems for exceptional situational awareness. Designed with angled surfaces to minimize radar visibility, these vessels are built for stealth. The spacious flight deck can support two SAH-60 Seahawk helicopters or multiple drones, offering diverse capabilities like airlift, rescue, and anti-submarine operations. Notably, in 2017, the USS Detroit made history as the first littoral combat ship to successfully test fire the AGM-114 Hellfire missile. The Navy has also put the Naval Strike Missile through its paces on the USS Coronado, officially selecting it as the primary anti-ship weapon for the LCS. The control system for the Independence class, developed by General Dynamics, employs an open architecture computing framework that enhances mission control and coordination. After early ships experienced significant corrosion issues, Austal implemented robust anti-corrosion measures on the remaining vessels. However, in May 2022, it was revealed that several Independence-class ships developed hull cracks above the waterline, particularly when traveling over 15 knots in rough seas. The Navy plans to address this by replacing the affected plates with thicker materials, assuring officials that these cracks do not compromise safety. In December 2014, the Navy's decision to base the small surface combatant on upgraded versions of the Independence and Freedom LCS marked another exciting chapter in naval innovation. This move aims to bolster firepower and protection. Austal proposed various enhancements, but the Navy opted to retain the 57mm gun while adding advanced radar and a new over-the-horizon missile system. Additionally, Austal has introduced the multi-role vessel, a smaller trimaran designed for border protection and anti-piracy missions. They also presented a more heavily armed design for the Navy's new frigate class, capable of carrying a range of missiles and anti-submarine technology, promising to elevate naval operations to new heights. Elon Musk's companies, particularly SpaceX and potentially his new aerospace venture, may or may not prioritize making sixth-generation fighter jets over national security and ethical considerations. Elon Musk is ambitiously venturing into aerospace with a sixth-generation fighter jet that promises to redefine aerial combat through groundbreaking technology and capabilities that seem almost otherworldly. Could this radical innovation render current military strategies obsolete? And what secrets lie behind the design and functionality of an aircraft that could change the face of modern warfare forever? Join us as we delve into Elon Musk revealing sixth-generation fighter jet that defies all physics. Elon Musk has not been directly involved in the manufacturing or designing of traditional fighter jets, nor has he launched a military aviation project with the aim of creating traditional fighter aircraft. His weight in aerospace and military circles grows from his visionary analysis of what the future of the skies in combat would look like, in addition to his general interest in space and rocket technology through SpaceX. Musk's comments about fighter jets went viral in 2020 when he told attendees at the Air Warfare Symposium that the era of manned fighter jets was over. He said the future of air combat would more than likely belong to autonomous, AI-powered drones capable of outrunning and outmaneuvering traditional fighters. The comments started to raise interest within the U.S. Air Force, raising hopes for unmanned aerial systems to take the dual role of companions and replacements for conventional fighters in certain missions. Musk has been blunt that fighter jet technology must be upgraded to accommodate unmanned systems that can fly on their own or function as wingmen to manned jets. He proposed developing competitive, AI-enhanced drones capable of challenging advanced fighters like the F-35. To Musk, such a method could push the boundaries of speed, agility, and decision-making that manned jets simply could never match because of human limitations. He further expanded this concept on social media to say that with a drone fitted with maneuvering autonomy, one could very easily outdo a piloted jet like the F-35, hence rendering it obsolete in many combat roles. That perspective underlines Musk's bigger belief in AI's potential to enhance decision-making and agility in critical situations, habits that have also shaped his contributions at Tesla and SpaceX. Musk's major contributions in the field of aerospace come through SpaceX, where he has managed to revolutionize rocketry with innovations such as reusable launch vehicles that drastically cut down on space mission costs. These two developments have made him an indispensable partner to NASA and the other military and government agencies concerned with space, further reinforcing the national security capabilities of the country in space. Under SpaceX, Musk initiated programs such as Starlink, a satellite-based internet service. Each one of these efforts has potential military uses, ranging from offering global communications coverage in remote and conflict-prone regions. This has placed him at the fulcrum of the debate on space-based defense, even if he is not directly getting into the manufacture of fighter jets. His views have catalyzed seminal discussions within the U.S. military, especially with regard to the NGAD program, a vision in which, later in the future, AI and autonomous drones would be able to carry out combat missions. While Musk does not fabricate fighter jets, his input about the considerations of defense and space innovations underlines a belief in the technological dividend, AI, and autonomy playing a strategic role in war. That has perhaps led military leaders to contemplate larger, high-tech, AI-driven air superiority for the decades to come. But in what ways has Elon Musk's work in the aerospace industry, through SpaceX and other ventures, potentially influenced or intersected with the field of military aviation? And what implications might his technological advancements hold for future military capabilities? Elon Musk's work in aerospace, particularly at SpaceX, relates to military aviation and developments on reusable rockets, satellite networks, and furthering military strategies. This has spinned around the orbits as a result of reusable rockets developed by SpaceX, such as the Falcon 9 and Falcon Heavy, making the launches of satellites cheaper and more frequent, thus increasing the options available to the military for access to space-based capabilities. These launches are used by the U.S. military to carry out vital missions in space, including secured communications, GPS, and surveillance, all significant components in its operations on air, land, and sea. It is this access to inexpensive and speedy deployment of satellites that reinforces national security and allows timely sets of orbital defense assets. Another huge contribution is SpaceX's Starlink, a global satellite internet network that will provide high-speed internet even in the most remote areas. Starlink has shown great potential for military use in establishing secure and resilient communication links in areas that are either remote or engulfed in conflict, where normal communications might either not be available or compromised. This network has already been tested for such purposes, which just goes to show the value it brings to deployed forces needing secure and stable communication channels in some really tough environments. Moreover, apart from this, Musk's ideas about the future of military aviation have influenced U.S. military strategy. He publicly submitted that autonomous drones could even outperform human-crewed fighter jets someday. He foresees the redefinition of air combat, where AI-powered drones attain the greatest of maneuverability and speed that no human-piloted aircraft is able to. This perspective has given birth to the deliberation within the U.S. Besides, the next-generation air dominance program of the Air Force also hopes to include autonomous drones as companions to manned jets. Musk's emphasis on AI-driven combat agrees with an Air Force increasingly interested in using drones for complex missions, potentially besides or instead of manned aircraft. SpaceX has emerged as a key player in the launch and operation of space-based defense assets for the U.S. Space Command. The assets serving national defense have also become critical due to their part in surveillance and early warning, extending military situational awareness into space. Similarly, with SpaceX, Musk extends the military's capability to monitor and respond to any new threats on the horizon, which could help reinforce defense capabilities for the U.S. and put the military in a better place for the complexities of space as a critical defense domain next to traditional air and land forces. With all this talk about the sixth-generation fighter jet, what unique and advanced technologies define this jet, and how do these features differentiate it from previous generations? A sixth-generation fighter jet is defined by a series of advanced technologies aimed at surpassing the capabilities of current fifth-generation jets like the F-35 or F-22. One major feature is advanced stealth and survivability. While fifth-generation fighters already emphasize low radar visibility, sixth-generation jets aim to further enhance stealth with advanced materials and thermal management techniques that minimize radar and infrared signatures. AI and autonomous systems also play a central role in sixth-generation jets, enabling capabilities that go beyond traditional piloted operations. These aircraft are expected to incorporate AI for autonomous decision-making, allowing them to handle threat analysis and control unmanned loyal wingman drones. This setup enables pilots to focus on broader strategic goals, leaving tactical adjustments and some in-flight operations to the AI. Another defining characteristic is sensor fusion and battlefield connectivity. Sixth-generation fighters will function as network nodes, sharing real-time data with other aircraft, drones, and ground systems. The seamless integration across platforms is intended to provide a more cohesive and comprehensive view of the battlefield, which is essential for complex, modern warfare scenarios that rely on quick, coordinated actions. Directed energy weapons are also expected to be part of these new jets, offering advanced defensive capabilities against incoming threats. These high-energy systems, such as lasers, may be used to counter missiles or other aerial threats, providing a potentially unlimited supply of ammunition in certain situations, unlike traditional munitions, which are finite. Additionally, sixth-generation jets are designed for long-range operations. Their ability to travel extended distances is crucial, especially for theaters like the Pacific, where operational ranges are vast. These aircraft will feature enhanced endurance, allowing them to conduct missions without frequent refueling support. Finally, enhanced agility and speed define sixth-generation jets, with adaptable engines capable of adjusting power and efficiency to suit various mission requirements. These engines facilitate high agility and sustained supersonic flight, known as supercruise. which is important for rapid deployment and response times in dynamic combat environments. Overall, sixth-generation fighter jets combine stealth, AI autonomy, advanced connectivity, directed energy options, and extended range to achieve superior air dominance in future combat scenarios. Seeing that these jets offer these many fantastic features, which countries are currently at the forefront of sixth-generation fighter jet development, and how are they each approaching the unique challenges and requirements of these new aircraft? Numerous nations are currently focusing on advancing sixth-generation fighter aircraft to secure air supremacy using state-of-the-art technologies. At the forefront is the United States, with its next-generation air dominance, also known as the NGAD initiative, that aims to develop a range of unmanned aircraft capable of functioning in challenging settings and anticipated to be operational by the 2030s. The next-generation air dominance model of the U.S. Air Force represents a forward-thinking approach to aerial combat by integrating piloted fighter aircraft with advanced drones, referred to as wingmen. This innovative design enables the manned fighter to work in concert with unmanned systems, enhancing situational awareness and operational effectiveness in complex environments. The wingmen drones are intended to carry out various tasks, such as surveillance, electronic warfare, and even direct engagement, allowing the piloted fighter to focus on more strategic objective. The United Kingdom is currently working with Japan and Italy on a project to create the Tempest fighter aircraft. This collaborative initiative is focused on launching a state-of-the-art sixth-generation plane by the mid-2030s. The Tempest fighter is anticipated to incorporate cutting-edge technologies, including intelligence features and directed energy weapons. Moreover, it will boast capabilities and multi-platform networking functions. Japan sees this partnership as an opportunity to strengthen its FX fighter program in alignment with its defense strategies in the Asia-Pacific region. In the 2040s ahead of us lies the Future Combat Air System, also known as FCAS, an effort between Germany, France, and Spain aiming to develop a cutting-edge combat system with both manned and unmanned components anchored by a sixth-generation fighter aircraft at its core. This initiative is set to integrate AI-powered command and control features, along with information exchange and adaptable weapon systems, to enhance the military prowess across Europe. China is also reportedly advancing its sixth-generation fighter, potentially evolving from its existing J-20 stealth fighter. Although details are limited, Chinese sources suggest it may feature AI-driven capabilities, hypersonic weapons, and further advancements in stealth technology, positioning it as counter to U.S. and allied developments. China aims to deploy its sixth-generation fighter by the mid-2030s, underscoring its commitment to competing in high-tech military aviation. Russia, too, is heavily invested in next-generation air combat technologies, which are believed to be an extension of its Su-57 program. Russian officials have indicated that their upcoming fighter will likely incorporate directed energy weapons, hypersonic capabilities, and advanced AI. Despite setbacks with the Su-57, Russia remains determined to advance its air combat technology and compete in the realm of sixth-generation fighters. Each of these national programs is focused on leveraging AI, autonomous systems, advanced connectivity, and directed energy options. This reflects a global shift towards multi-platform, networked air combat designed to operate in contested environments, ultimately aiming to deliver a strategic advantage. These jets, although advantageous, have their disadvantages. But what are some of the significant drawbacks and challenges that come with the development and deployment of sixth-generation fighter jets, including financial, technological, and ethical concerns? And how might these factors impact the future of these programs? What makes sixth-generation fighter jets so enticing is that they are expected to bring revolutionary performances to the fight. But it also means that these fighter jets have a number of inherent disadvantages. One eliciting factor is the high development and operational costs of these networks. These jets demand heavy capital investment. Costs are further exacerbated by the incorporation of high-end technologies such as AI autonomy, directed energy weapons, and the use of advanced composite materials. For example, the next-generation air dominance fighter in the U.S. Air Force will most probably command prices of $300 million or even more per unit, making the series probably a low one. This would place pressure on defense budgets and limit fleet numbers, making them an expensive solution to national security. Related to the first point, there is also the issue of having to maintain and control complex technology. Sixth-generation fighters are highly dependent on untested, sophisticated systems like AI-powered autonomy and extensive networking for data sharing and communication. Although these technologies increase awareness on the front lines, they come with weaknesses. The important networks could be hacked or experience other failures that affect their performance and could expose aircraft to threat. Another difficulty of the sixth-generation development is the security and stability of corresponding technologies as they become more sophisticated. The feature is also important because advanced capabilities of the jets mean that pilots need to undergo elaborate training. For using sixth-generation aircraft, a pilot is not only required to maneuver his aircraft, but also a loyal wingman drone and handle the systems that are AI-enabled. This double-skill approach causes a lot of training, and training is synonymous with cost and time. Such specialized training could put a constraint on the number of talented pilots that are available, thereby having an effect on the overall readiness of those air forces armed with such aircraft. However, issues concerning maintenance and logistics are operational hurdles because of the complex nature of assimilated materials and systems in the sixth-generation fighters. Technological devices such as adaptive engines, stealth coatings, and directed energy weapons need special care in terms of maintenance, which would, in turn, result in longer durations of maintenance and the attendant high costs. The complexities involved in repairing these systems may also require advanced facilities and specialized personnel, making maintenance a costly and time-intensive process compared to previous generation fighters. Finally, the introduction of autonomous and AI systems brings ethical and strategic risks. Autonomous drones and AI-assisted systems have the potential to make decisions independently, which raises ethical concerns around human oversight in lethal operations. There's also a strategic risk in relying on autonomous systems, as any malfunction, misinterpretation, or hijacking of these systems could lead to unintended engagements and even escalate conflicts. These ethical and operational uncertainties add another layer of complexity to the deployment of sixth-generation jets. In conclusion, those statements reveal that, despite substantial potential benefits, sixth-generation fighters generate many financial, logistic, and ethical concerns that might diminish the efficacy of these solutions and provoke queries concerning the human role and autonomy in aerial combat systems. As sixth-generation jets are designed to incorporate AI and autonomous capabilities, will they work in partnership with drones or eventually replace them? Elon Musk has not personally taken part in the direct advancement of sixth-generation fighter jets. However, he has opined heavily on what the future of aerial warfare looks like and the incorporation of drones into the model. This is something that Musk believes will continue to play out within air combat, pegging his bets on drones, especially those driven by artificial intelligence. Speaking during various forums, including the Air Warfare Symposium in 2020, he argued that towing the line of manned fighter jets is on its way out. Despite this, he argued that unmanned aerial vehicles or drones may be better manned jets, referring to the speeds, quick decisions, and agility limitations of human pilots. In his vision, Musk has brought up the idea that drones can act both as wingmen to the traditional fighter jets and maybe even replace the latter in some way. He sees the possibility for drones as supplementary machines for manned aircraft or as combat machines separate from manned aircraft, which would provide more opportunities for maneuver and less risk for pilots. Even though Musk's companies are not creating regular fighter jets, some of the technology and capabilities engaged by SpaceX and other related companies have an application to military aviation. SpaceX is known for mechanically recyclable rockets and artificially intelligent systems for orientation and choice. These innovations could be used as a basis for the creation of the new fully or partly unmanned military drones. Moreover, Musk's focus has repercussions for drones, as he supports the use of AI in military systems by stating that it improves their performance and function. Musk must have seen utility in drones as a subset of his general fascination with the use of technology as a tool to solve complex problems. To him, self-directed systems are ways of improving military capability and at the same time reducing human dangers. This aspiration for advancing AI technologies in both private and Army sectors is concise, with volumes of pushing the limits in IVF success rates. Musk has caused debates in the military circles, including in the United States Air Force, over the use of unmanned aerial vehicles in the future airborne combat systems. They helped to discuss the Next Generation Air Dominance Program and other similar programs. While the sixth-generation jets do not involve Musk and his companies as producers, his concept of future air combat emphasizing drones will likely change the strategic use of the air forces. Musk's creative visions, especially via SpaceX and other allied native space firms, can bring revolution in specific observation of aerial warfare, emphasizing on drones and AI. This turn toward the further adoption of drones is not only an academic discussion to discuss, it is an ongoing evolution within the military hierarchies that may alter the character of warfare. A $200 million military eye might be watching you right now from 60,000 feet in the sky. The RQ-4 Global Hawk, with its ability to capture images so detailed, read information from 12 miles up, and track 12 moving targets simultaneously, is revolutionizing aerial warfare. Is this the future of warfare and civilian surveillance? And what is the big deal with this cutting-edge technology that even Elon Musk is eager to explore? Join us as Elon Musk explores the world's largest $200 million drone. In the 1990s, while most Americans were buzzing about the internet and grunge music, the United States Air Force was quietly shaping the future of aerial reconnaissance. Two remarkable aircraft emerged from this era: the sleek, stealthy Lockheed Martin RQ-3 Dark Star and the high-flying Global Hawk. When budget constraints forced military leaders to choose between the two programs, they made a pivotal decision. Despite Dark Star's impressive stealth capabilities, the Global Hawk's exceptional range and substantial payload capacity won the day. The Global Hawk took its maiden flight on February 28, 1998, at Edwards Air Force Base, California. But this wasn't just another military test flight. The demand for its capabilities was so urgent that the Air Force made an unprecedented move. They began using prototype aircraft in actual combat operations in Afghanistan, while the plane was still being developed. The initial version, known as Block 10 or RQ-4A, proved so successful that 9 were produced. 2 of these found their way to the United States Navy, while others were deployed to Iraq, demonstrating the aircraft's versatility in different combat environments. But the team behind Global Hawk wasn't content to rest on their laurels. They went back to the drawing board and redesigned the airframe, stretching both the nose section and wings. This enhanced version, dubbed the RQ-4B Block 20, could carry an impressive 3,000 pounds of internal payload, which is more than twice its predecessor's capacity. The first Block 20 aircraft, marked as the 17th Global Hawk ever produced, rolled out during a ceremony on August 25, 2006. After its first flight from USAF Plant 42 in Palmdale to Edwards Air Force Base, on March 1, 2007, the aircraft underwent extensive testing throughout 2008, paving the way for its future role as one of the military's most valuable surveillance assets. While the Global Hawk was making waves in the Air Force, the United States Navy saw an opportunity that would revolutionize maritime surveillance. But could this aerial giant adapt to life at sea? The Navy's journey with the Global Hawk began when they acquired 2 Block 10 aircraft, giving them special designations N1 and N2. After brief testing in California, the aircraft moved to Naval Air Station Patuxent River in March 2006 for an ambitious program called the Global Hawk Maritime Demonstration. The true test of its maritime capabilities came in July 2006 during the Rim of the Pacific exercise, the world's largest international maritime warfare training event. Operating from Point Mugu, California, the Global Hawk demonstrated its exceptional endurance by flying roughly 2,500 miles each way to patrol the waters near Hawaii. During 4 remarkable flights, it provided over 24 hours of non-stop surveillance, working alongside the aircraft carrier USS Abraham Lincoln and the amphibious warfare ship USS Bonhomme Richard. The Navy was so impressed with the Global Hawk's performance that they decided to develop their specialized version. In 2008, they awarded Northrop Grumman a $1,160,000 billion contract to create what would become the MQ-4C Triton. This new variant wasn't just a copy of its Air Force cousin. It was specifically engineered for the unique challenges of maritime operations. The Triton's wings tell the story of its special capabilities. While the Global Hawk typically stays at high altitude, the Triton can swoop from 50,000 feet down to 10,000 feet to get a closer look at suspicious vessels. Its reinforced wings feature anti-icing systems and can withstand both lightning strikes and bird impacts, essential features for an aircraft operating in unpredictable maritime environments. The Navy's confidence in the platform was proven during a remarkable 13-year deployment in the Middle East, where their Global Hawks flew over 2,000 missions and logged more than 42,500 flight hours. This success paved the way for the Triton to become the Navy's premier maritime surveillance platform. After proving its worth in maritime operations, the Global Hawk program faced a storm of its own. But would skyrocketing costs and budget battles ground this revolutionary aircraft before it could reach its full potential? By mid-2006, alarm bells were ringing in Washington. The cost per aircraft had soared 25% above initial estimates, largely due to necessary design improvements and capability upgrades. Congress began questioning whether the program's national security benefits could justify its growing price tag. The situation became so serious that the entire project risked cancellation. The Air Force responded by restructuring the program in June 2006. They pushed back the completion of a crucial operational assessment report by 2 years and extended production timelines to 2015. But the challenges didn't end there. In February 2011, the Air Force cut their planned purchase of advanced Block 40 aircraft in half, from 22 to just 11, to control costs. A major turning point came in June 2011, when the Secretary of Defense made a bold declaration. The Global Hawk was critical to national security. The numbers back this up. It costs $220 million less per year to operate than the legendary U-2 spy plane on comparable missions. Plus, the Global Hawk could carry sensors that the U-2 couldn't handle simultaneously. Between 2010 and 2013, the program achieved a remarkable turnaround. The cost per flight hour plummeted by more than 50%, dropping from $40,600 to $18,900. This dramatic reduction was partly due to increased usage. By 2018, the Air Force had received 287 out of 366 ordered aircraft, with plans to eventually acquire 433 Global Hawks, including foreign military sales. However, in July 2022, a surprising announcement revealed plans to retire the Global Hawk by 2027, though not before it would pioneer new roles in testing hypersonic missiles and other advanced technologies. While budget battles raged in Washington, the real story of the Global Hawk's power lay in its extraordinary suite of sensors and systems. But what exactly makes this giant drone one of the most sophisticated eyes in the sky? At the heart of the Global Hawk's capabilities is its integrated sensor suite, a collection of advanced tools that work together like a high-tech Swiss Army knife. The system combines 3 powerful sensors: a synthetic aperture radar, an electro-optical camera, and an infrared sensor. Working together, these sensors can spot objects on the ground as small as 12 inches across from an altitude of 20 kilometers. The drone's radar system is particularly impressive. In wide area mode, it can scan an area of 62 miles in radius, searching for moving targets. When it needs a closer look, it can switch to spot mode, providing detailed images of smaller areas with incredible clarity. Think of it like switching from a wide-angle lens to a powerful zoom on a camera. But seeing isn't enough. The Global Hawk needs to share what it discovers. That's where its sophisticated communication systems come in. Using military satellite links and ground stations, it can transmit data in real time to commanders and analysts anywhere in the world. 2 ground elements make this possible: the launch and recovery element for takeoffs and landings, and the mission control element for managing the actual mission. In 2019, the system got even better with the addition of a new weather radar. This upgrade allows the drone to detect turbulence, track storm development, and navigate safely through challenging weather conditions. Crucial abilities for an aircraft that sometimes needs to stay airborne for over 30 hours straight. Perhaps most impressive is its ability to operate autonomously. While pilots on the ground can take control when needed, the Global Hawk can fly pre-programmed missions by itself using GPS and internal navigation systems to find its way, even in areas where GPS might be blocked or jammed. With its cutting-edge technology and remarkable capabilities, the Global Hawk was ready to prove itself in real-world operations. But could this technological marvel change the course of history through its unprecedented achievements? The Global Hawk's most dramatic demonstration came on April 24, 2001, when it made history by becoming the first unpiloted aircraft to cross the Pacific Ocean. Flying from Edwards Air Force Base in California to RAAF Base Edinburgh in Australia, the drone covered an astounding 8,214 miles in just 22 hours. A world record for unmanned aircraft distance that showcased its incredible range and reliability. But the Global Hawk wasn't done setting records. On March 22, 2008, it shattered endurance expectations by staying airborne for 33.1 hours at altitudes up to 60,000 feet, higher than most commercial airlines ever fly. It's like having a tireless sentinel in the sky, able to watch over an area the size of Illinois for more than a day without needing to land. The drone's real impact became clear in combat zones. By September 2013, the Global Hawk fleet had amassed 100,000 flight hours, with 88% of those missions supporting military operations in Afghanistan, Iraq, and Libya. To put this in perspective, that's equivalent to more than 11 years of continuous flight. In just one remarkable week in September 2014, the fleet flew 781 hours, nearly a month's worth of surveillance packed into 7 days. But the Global Hawk's value extended far beyond military operations. When disaster struck, it proved to be an invaluable tool for humanitarian missions. After the devastating 2011 Tohoku earthquake and tsunami in Japan, Global Hawks flew 300 hours over the affected areas, helping authorities assess damage and coordinate relief efforts. They even assisted in monitoring the dangerous situation at the Fukushima Daiichi nuclear power plant. Its capabilities were further demonstrated during search and rescue operations. In 2014, a Global Hawk joined the search for kidnapped Nigerian schoolgirls, working alongside other aircraft to scan vast areas of difficult terrain. During Hurricane Earl in the same year, these drones provided critical data about storm development and movement, helping meteorologists make more accurate predictions. However, not all missions ended successfully. In June 2019, tensions rose dramatically when Iran shot down a United States Navy Global Hawk over the Strait of Hormuz. While the United States maintained the aircraft was in international airspace, the incident highlighted the risks these valuable assets face in contested regions. The longest combat mission ever flown by a Global Hawk lasted 32.5 hours, nearly a day and a half of continuous operation. This incredible endurance, combined with its ability to operate in various environments and missions, established the Global Hawk as one of the most versatile and capable surveillance platforms ever created. After setting numerous records and proving its worth in military and humanitarian missions across the globe, the Global Hawk was about to embark on perhaps its most exciting mission yet. But could this retiring warrior find an even more crucial role in advancing America's hypersonic future? The Range Hawk is a fascinating transformation of the Global Hawk that's giving retired military drones a second life in testing America's newest and fastest missiles. The Department of Defense's Test Resource Management Center came up with an ingenious plan. Instead of letting these sophisticated aircraft gather dust, why not use them to track and monitor hypersonic missiles? Currently, testing hypersonic weapons requires specially equipped ships. It takes about 3 weeks to position and prepare a ship for a single test, limiting the program to roughly 12 tests per year. But the Range Hawk program aims to change all that dramatically. By converting Global Hawks into Range Hawks, engineers are creating a more flexible and responsive testing system. These modified drones can be ready to fly much faster than ships can be positioned, potentially allowing for weekly hypersonic tests, a game-changing improvement in development speed. Plans are underway to convert 4 Block 20 and 20 Block 30 airframes that have been retired from Air Force service. That's 24 high-tech platforms dedicated to advancing hypersonic technology. Early results are already proving impressive. In 2023, converted Block 10 Range Hawks supported 10 hypersonic flight tests, including 2 tests just 10 days apart, something that would have been impossible with ship-based monitoring. These tests, conducted over both the Atlantic and Pacific Oceans, demonstrated the system's flexibility and rapid response capabilities. While the Range Hawk program points to an exciting future for these remarkable aircraft, understanding the raw power and capability packed into each Global Hawk reveals why it's such a versatile platform. But what exactly makes this technological marvel soar above the rest? At first glance, the Global Hawk's dimensions are jaw-dropping. It is a plane with wings stretching 131 feet wider than a Boeing 737 airliner. Standing nearly 15 feet tall and measuring 47 feet from nose to tail, this isn't your average drone. In fact, it's one of the largest unmanned aircraft ever built. The heart of this aerial giant is its Rolls-Royce AE3007 turbofan engine, producing an impressive 7,050 pounds of thrust. Think of this as having the power of 7 high-performance sports cars packed into a single engine. This power plant allows the Global Hawk to climb to altitudes of 60,000 feet, more than 11 miles up, where the air is so thin that most aircraft can't fly. Despite its massive size, clever engineering keeps the aircraft relatively light. The fuselage is built from aluminum, using a semi-monocoque design, a fancy way of saying it's like a strong shell that distributes weight and forces evenly. The wings are made from advanced composite materials, similar to those used in Formula One race cars, providing strength while keeping weight down. When it comes to carrying capacity, the Global Hawk is a heavyweight champion in the drone world. The RQ-4B can haul up to 3,000 pounds of internal payload. That's about the weight of a small car while still having room for 4,000 pounds of fuel. This combination gives it the ability to stay airborne for up to 32 hours while carrying a full load of surveillance equipment. Speed isn't sacrificed either. The Global Hawk can cruise at around 310 miles per hour while operating at its typical altitude of 65,000 feet. At this height, it can survey an area the size of South Korea in just 24 hours, capturing images so detailed they can identify objects as small as a laptop computer on the ground. The latest variant, the MQ-9B Sky Guardian, pushes these capabilities even further. With a maximum takeoff weight of 12,500 pounds and 9 hardpoints for carrying equipment, it's designed to stay aloft for over 40 hours. That's like flying from New York to Los Angeles and back twice without landing. Perhaps most impressive is its range of 6,900 miles without refueling. To put this in perspective, that's enough to fly from New York to Tokyo with fuel to spare. This exceptional range, combined with its payload capacity and endurance, makes it perfect for missions requiring long-term surveillance or monitoring. The aircraft's physical design also includes smart features like anti-icing systems, lightning protection, and the ability to withstand extreme weather conditions. These capabilities, combined with its sophisticated avionics and communication systems, ensure it can operate effectively in almost any environment, from Arctic cold to desert heat. However, there are a few more that are just as exciting as the RQ-4. Have you ever noticed how technology seems to grow bigger and more capable with each new generation? Just like how smartphones evolved from simple cell phones, the MQ-1 Predator and MQ-9 Reaper represent the same kind of evolution in drone technology. Think of the Predator as the pioneering older sibling and the Reaper as its bigger, stronger younger brother. Size is the most obvious difference. The Predator is relatively compact, with a 48-foot wingspan and a length of 27 feet. The Reaper, however, is significantly larger, stretching 36 feet long with wings spanning nearly 66 feet. This bigger size isn't just for show. It allows the Reaper to carry much more equipment and stay in the air longer. Power is another major difference. The Predator uses a modest 115 horsepower engine, similar to what you might find in a small car. The Reaper, by comparison, packs a much stronger 950 horsepower turboprop engine, letting it fly faster and carry heavier loads. While the Predator cruises at about 84 miles per hour, the Reaper can zoom along at 170 to 200 pounds. When it comes to carrying capacity, the differences are striking. The Predator can carry about 450 pounds of equipment, while the Reaper can haul up to 3,800 pounds, more than 8 times as much. This means the Reaper can carry more fuel, cameras, and equipment for different types of missions. Flight time is crucial for these aircraft. The Predator can stay airborne for about 24 hours, which was impressive when it first flew. The Reaper pushes this even further, with some versions able to stay up for 42 hours with extra fuel tanks. The Predator served faithfully from the 1990s until 2018, when the Air Force retired it in favor of the Reaper. This transition marked a significant leap forward in drone technology, similar to upgrading from a reliable family sedan to a powerful SUV. Both aircraft changed how we think about unmanned flight, but the Reaper took everything that made the Predator successful and made it better, bigger, and more capable. The USS Gerald R. Ford, renowned as the world's most advanced aircraft carrier, might also be the Navy's most expensive failure, with billions of dollars spent on unproven technology that may leave it vulnerable in real-world combat. This vessel reliability is now being questioned. Can the USS Gerald R. Ford overcome its technical challenges to fulfill its promise as the world's most advanced carrier? And given the rise of sophisticated missile technology from rival powers, can it truly defend itself against next-generation threats? Join us as we delve into the U.S.'s testing of all-new gigantic $13 billion aircraft carrier. The U.S. Gerald R. Ford Series CVN-78 aircraft carrier is the first of its kind in the Ford class. It is equipped with innovative technologies meant to enhance the performance, capability, and durability of the ship. Leading the way as the first of her kind, the Ford class presents innovations that are revolutionary when compared to the Nimitz class, and thus is the first in a new generation of aircraft carriers. The majority of the significant changes in the Ford class of carriers are represented by the electromagnetic aircraft launch system, also known as EMALS. While some catapult systems still use steam to launch the aircraft, the EMALS uses electromagnetic fields instead, which is much more efficient and takes a minimal toll from the aircraft. This design system implies some future advantages of launches that are quicker and smoother to execute, which can contribute to a higher readiness level. Another is the Advanced Arresting Gear, also known as AAG, since it is intended for the accomplishment of the recovery of the incoming aircraft using energy absorption technology. This characteristic makes the Ford capable of accommodating more aircraft weights and flexibility in terms of missions. The AAG is developed to reduce mechanical stress when touching down, to enhance the quality and safety of a landing, while putting less pressure on the aircraft. By emphasizing the flexibility and durability of the equipment, the AAG contributes to the enhancement of the flexibility of the carrier that enables it to accommodate various types of aircraft with a higher level of accuracy. The Ford contains the generation known as dual-band radar, also known as DBR, where one radar does the functions for all the other different types of radar, making it easier to detect and track threats such as missiles and aircraft. This integrated radar setup is supposed to enhance the limitations of multiple threat scenarios and response accuracy for the carrier. Realizations that include the advanced weapons elevators are part of this efficiency in which munitions are moved to the flight deck at faster rates, hence increasing the readiness and responsiveness of the carrier during high-demand situations. The technological advancements jointly imply improving the effectiveness of operational utilization of the Ford-class carriers with proper organization of manpower and resources. With this new craft comes some major concerns. So what new concerns have arisen with the application of these new technologies to the Ford carriers? And how can the need for carriers be met and the challenges mitigated? The Navy's trials with EMALS and AAG on the USS Gerald R. Ford provide some valuable lessons in reliability engineering, showing that these challenging conditions, far from being exceptional, are in fact typical for contemporary naval operations. EMALS and AAG are new-age technologies aimed at accomplishing the job of customary steam-propelled catapult and hydraulic arresting gear in aircraft carriers. Whereas EMALS provides steamless electromagnetic forces to catapult planes into the air, AAG employs ultra-high energy absorption to arrest incoming aircraft for a smooth touchdown. Combined, they provide for enhanced takeoff and landing profiles with better turnaround times, which provides flexibility within Fenton's fleet to accommodate a broad range of airplanes. Nonetheless, experiments have revealed that some of these systems perform suboptimally to their operational requirements. However, in this respect, the System Enhanced Integrated Lifting System has been referred to as EMALS and revived with the Allied System of Annex as AAG, which is not always able to address the Navy's concern of achieving a high number of launches and recoveries with no faults or failures. For instance, in the case of EMALS, There have been problems with power load distribution and its general reliability, which sometimes result in shutdowns. While such faults may present themselves during other spacecraft launch phases, they can be especially damaging during launches due to their potential to disrupt a flight's timeline, diminish a mission's efficiency, or endanger aircraft and crew on board. It is worthy to note that at the time of carrying out these functions, the AAG has as well encountered its own reliability issues. Approved to accommodate a larger variety of payloads, from the lightweight UAVs to heavy fighter jets, AAG every now and then fails in operation tests, especially if used constantly. These problems add stress to maintaining aircraft and decrease the time actually available for flight utilization, thus lowering the sorties, missions per day/shift, that a ship can launch and recover. Due to these reliability issues with EMALS and AAG, the Navy has been forced to undertake reliability reviews and reliability improvements. Skill film technical deficiencies. Engineers and technicians are in the process of developing ways on how to improve the functional capabilities of these systems so as to achieve the extended operational need in terms of strength and reliability. A key purpose is to make certain that at any given time, EMALS and AAG are capable of providing support to the carrier's high operational tempo without closing up or coming to a standstill for repairs. Originally unveiled in 2017, the ship's defense systems, and most importantly, the radar and missile interceptors that are part of the air defense system of the USS Gerald R. Ford, are instrumental in covering the carrier and its complement, in addition to vessels in its company, against various threats ranging from missiles, drones, and aircraft. There are these systems that are specifically designed to not only identify threats and threats coming in, but to arrest and defeat them. But in general, the defense of the Ford has been questioned simply due to a variety of tests that showed some weaknesses on their part. The DBR, or dual-band radar, is also part of the defense system to track numerous types of threats at once. Implemented as a single system, the DBR combines a number of radar functions, which theoretically at least provides the carrier with improved surveillance, response time, and efficacy. In the tests, the DBR has been demonstrated to be effective at tracking threats and giving the Navy important information about the speed, direction, and type of impending perils. Nevertheless, some drawbacks in simulations where several threats are present simultaneously, or where the threats may differ in kind, have been reported, such as differing between missiles and low-flying UAVs. This has given rise to the worry of whether radar is capable of managing complex events that would probably require the different dangers targeting the carrier to be addressed at the same time. In most cases, the targeting sensors that are utilized in the targeting process deliver good results in detection and tracking of target objects. However, there are some circumstances during the testing when interceptors cannot effectively fire or destroy the simulated targets. These failures indicate possible weaknesses in an approach to the carrier's multifaceted shield that should involve a number of layers designed to identify, track, and eradicate threats. Those concerns are being met by the Navy performing its due diligence, evaluating where and if improvements need to be made in order to get the most out of the Ford class's already strong defenses. Current efforts are being made by engineers to advance the radar's tracking signalization and concern the DBR with other anti-missile weaponry parts in order to respond to compound threats under intense conditions. The Navy's aim is to prove that every weapon system of the Ford is fully capable of achieving this firing solution against a variety of realistic threat scenarios that may be encountered by a flat top when it is committed to active operations. Therefore, how does this new Ford-class carrier's power and energy system differ from Nimitz-class or other older aircraft carriers? And what are the implications of these differences for current operations and efficiency or future capability? The Ford-class aircraft carriers are equipped with an advanced nuclear reactor system that produces approximately 3 times the power of the previous Nimitz-class carriers. This immense energy capacity is one of the defining features of the Ford class, enabling the ship to support a broader range of high-demand technologies and advanced weapon systems. The increased power output, around 125 megawatts, is critical for meeting not only the carrier's current operational needs, but also for accommodating future advancements in naval technology. One of the most exciting implications of this enhanced energy capacity is its potential to support next-generation defense systems, such as laser-based weaponry. Unlike conventional weapons, which rely on ammunition, Laser weapons consume only energy, making them a sustainable and cost-effective option for intercepting threats like missiles and drones. The Ford-class carrier's surplus energy could power these systems continuously without overburdening its reactors, giving the ship the capability to defend itself against multiple high-speed or high-volume threats. This could be especially advantageous as the nature of naval threats becomes more advanced and varied, with potential adversaries deploying faster, smaller, and more numerous missile systems. In addition to laser-based defenses, the Ford-class carriers are well-positioned to integrate other energy-intensive systems that may emerge in the future. Electromagnetic railguns, for instance, require substantial power to launch projectiles at speeds far exceeding those of traditional explosives. Railguns would provide the carrier with a long-range, high-velocity strike capability that could target both air and surface threats with unparalleled precision. The increased power capacity of the Ford class means that it could support such systems without compromising other essential operations, allowing the carrier to maintain its role as a powerful offensive and defensive asset. These systems provide comprehensive situational awareness, a critical advantage in modern naval warfare, where fast response and adaptability are essential. The energy surplus also opens up possibilities for supporting emerging technologies like artificial intelligence and autonomous drones, which demand substantial processing power and energy. To sum it up, the Ford class's energy capacity serves as a future-proofing measure, allowing it to incorporate new technologies over its lifespan of 50 years or more. This adaptability ensures that Ford-class carriers can evolve in response to rapidly advancing military technologies and shifting defense strategies, making them a resilient platform for modern and future warfare. How do U.S. allies and partners perceive the deployment of the USS Gerald R. Ford, and what does that say about greater ramifications for international military cooperation and strategic partnerships? Recent deployments of the USS Gerald R. Ford to Europe have been more of strategic missions than purely an operational exercise, showing how serious the U.S. is concerning its defense commitments in partnership with NATO allies when geopolitics are heating up. The U.S. places the Ford in European waters. The Navy stresses the principle of collective security and pledges the allied nations continued assistance against regional threats, particularly in those cases when the adversarial presence or action may be challenging the stability. While in Europe, the Ford has performed numerous joint training exercises with NATO forces, this being an opportunity for the carrier and her crew to work directly with other allied naval units. This kind of collaboration represents really useful training for all the participating forces to perfect the joint operational tactics, share strategic intelligence, and foster interoperability between myriad military branches and technologies. Working with NATO allies in exercises such as air defense drills, anti-submarine operations, and maritime security simulations, the Ford helps to standardize procedures among those nations so they'll be able to operate together if a real-world conflict ever comes up. The presence of the Ford also represents strength and unity within the NATO alliance. To be in a position to host one of the most advanced aircraft carriers with allied fleets is a very strong message that NATO still remains formidable in protection and defense of its membership and values shared among its membership. This will enhance deterrence by underscoring the collective defense capability that would respond to hostile action. It is also a visible reminder of the capabilities and cohesion of NATO, a factor of dissuasion of hostile acts, because it shows that the alliance is ready and willing to react together against any threat. Besides reinforcing military cooperation, such deployments are an opportunity for the Ford and its crew to gain experience in operations under various environmental conditions, as well as with other NATO forces. Cross-training with NATO forces provided valuable exposure to the protocols and procedures of allies, furthering a deeper level of mutual understanding and respect between the forces, a necessity toward effective joint operations. That integration of advanced Ford capabilities with those of NATO allies ensures that the deployment further enhances the readiness of the alliance against both conventional and non-conventional threats, now and into the future. Given that each Ford-class carrier costs around $13 billion, how do the projected operational savings and efficiencies translate into overall cost-effectiveness throughout the carrier's expected service life? The USS Gerald R. Ford's construction, costing approximately $13 billion, marks it as the most expensive warship ever built. This significant investment reflects Ford's advanced capabilities and the extensive research and development efforts required to incorporate next-generation technologies. Although the price tag has been met with scrutiny, the Navy believes that the long-term operational savings will justify the initial expense by reducing overall lifecycle costs, making the carrier cost-effective over its expected 50-year service life. One of Ford's major cost-saving features is its smaller crew size. The Ford-class carriers are designed to operate with around 20% fewer personnel than the Nimitz-class carriers, reducing the crew from about 5,000 to approximately 4,000, including air wing personnel. This reduction is possible due to the automation and efficiency improvements embedded in the ship's systems. Automated weapons elevators, advanced digital controls, and more efficient shipboard processes help streamline tasks that traditionally required more manual labor. Fewer crew members mean lower personnel costs such as wages, benefits, and training, which are substantial portions of the overall operational budget. Over time, this lighter crew requirement is expected to generate significant savings. Another major area of projected savings lies in the extended periods between maintenance overhauls. The Ford-class carriers are built with more durable and efficient systems designed for extended operational availability. For instance, the Ford's nuclear reactors have an extended life cycle, allowing the ship to operate continuously for longer periods before needing major refueling and maintenance. This enables the Ford to spend more time deployed or in active service and reduces the frequency and cost of lengthy, costly maintenance periods that traditionally took Nimitz-class carriers offline. This increase in operational availability maximizes Ford's service time while minimizing downtime costs. Ford's fuel efficiency further contributes to its cost-effectiveness. Although nuclear-powered carriers do not require traditional fuel, they still rely on large amounts of fuel for their aircraft and other onboard systems. Beyond these cost-saving features, the Ford's design also anticipates future upgrades and modernization efforts, allowing new technologies to be integrated more easily and cost-effectively. The ship's modular construction and increased energy capacity are intended to simplify the addition of future systems, such as laser weaponry or advanced radar, without requiring extensive retrofitting. This flexibility lowers the financial burden of keeping the ship technologically current, extending its relevance over the decades, and potentially avoiding the need for entirely new carriers sooner than expected. In what ways does the training of crews for the USS Gerald R. Ford differ from that of previous aircraft carriers? And how do these changes reflect the integration of advanced technologies and operational requirements unique to the Ford class? Training programs for the crews of the Ford-class aircraft carriers have undergone significant updates to align with the advanced technologies integrated into these modern vessels. As the USS Gerald R. Ford incorporates systems like the Electromagnetic Aircraft Launch System, EMALS, the Advanced Arresting Gear, AAG, and various integrated combat systems, the need for specialized training has become paramount. These systems represent a shift from traditional naval operations, necessitating a comprehensive approach to ensure that crews are fully equipped to operate and maintain these cutting-edge technologies effectively. The training curriculum now places a strong emphasis on the operational aspects of EMALS and AAG. EMALS, for instance, replaces the conventional steam catapults used in older carriers, requiring crews to adapt to new procedures for launching aircraft. Training programs include hands-on simulations that allow personnel to practice launching a variety of aircraft under different conditions, familiarizing them with the system's controls and emergency protocols. This immersive approach helps build confidence in using EMALS, ensuring that crews can execute launches efficiently and safely during real-world operations. Similarly, the Advanced Arresting Gear requires specific training to handle the complexities of recovering aircraft. The AAG system utilizes energy-absorbing technologies that differ significantly from previous hydraulic systems. Crews must understand the mechanics of the AAG, including its various components, and how to troubleshoot potential issues during recovery operations. Training exercises include simulated landing scenarios that replicate the dynamic conditions of actual flight operations, allowing personnel to experience the nuances of the AAG in a controlled environment. Furthermore, the training programs have been designed to incorporate integrated combat systems that enhance the carrier's defensive and offensive capabilities. These systems include advanced radar, missile defense, and communication technologies that allow for real-time data sharing and situational awareness. In addition to hands-on training, the Ford-class training programs leverage virtual reality, VR, and computer-based simulations to create realistic operational environments. These technologies provide crews with opportunities to experience various scenarios without the risks associated with live exercises. By using VR, personnel can engage in emergency drills, practice routine operations, and gain familiarity with the ship's layout and systems before stepping aboard the actual vessel. This innovative approach enhances retention and comprehension, ensuring that crews are better prepared for their responsibilities. The emphasis on updated training programs reflects a broader commitment to ensuring that the Ford-class carriers can operate at peak efficiency from day one. By investing in comprehensive training tailored to the unique technologies of the Ford, the Navy aims to maximize operational readiness and minimize the potential for errors during critical missions. As the Ford-class carriers enter service, the effectiveness of these training initiatives will be vital in determining how well the crews can leverage the ship's advanced capabilities to meet modern naval challenges. Ultimately, this thorough preparation will contribute to the overall mission success of the Ford-class carriers as they engage in strategic deterrence, power projection, and allied operations in a rapidly evolving global security landscape. Israel has just unveiled a secret weapon that's taken the world by surprise. In a region where missile technology is advancing quickly, Israel has introduced a game-changing hypersonic missile that's faster, more accurate, and more powerful than anything seen before. This missile can strike in minutes, leaving other nations on high alert. What makes this hypersonic missile so powerful? And how could it reshape Israel's place in the world? Join us as we reveal the impressive features and hidden details behind Israel's new hypersonic missile that shocked countries like Hamas, Iran, and Russia. Israel's secret hypersonic missile has surprised its neighbors and rivals alike, raising concerns across the region. For years, Israel has faced countless threats, from short-range rockets to complex missile systems. Each new challenge pushed Israel to develop stronger defenses, leading to the breakthrough of this advanced missile technology. Recently, Israel introduced the Sky-Sonic, an advanced hypersonic missile interceptor, and it's got everyone's attention. This hypersonic missile is faster and harder to track than anything before it, as it could change the balance of power in the region. It is designed to respond quickly and precisely, making it a new level of defensive power in Israel's defense. With the ability to track and hard to detect, it can destroy targets moving at hypersonic speeds. Hypersonic missiles move at speeds over Mach 5, making them challenging for any defense system to track, let alone intercept. With Sky-Sonic, Israel has joined the group of nations tackling the challenges of these ultra-fast missiles. Unlike traditional defense systems, which struggle to keep up with this speed, this powerful missile was designed from the ground up to locate, lock onto, and intercept hypersonic threats. The technology behind this advanced missile is what makes it so impressive. It uses advanced tracking and artificial intelligence to predict and intercept targets moving at incredible speeds. Its radar systems and tracking algorithms allow it to calculate the exact location and speed of a hypersonic missile, setting up an interception before the missile even reaches its target. Its incredible speed makes it effective against hypersonic missiles, as it is fast enough to catch up with traditional missiles due to its accurate tracking. It is built to reach speeds that allow it to intercept missiles that would evade standard defenses, giving Israel a powerful shield against these advanced threats. Hypersonic missiles can travel at altitudes and velocities that allow them to evade standard radar and tracking methods. Sky-Sonic has been specifically engineered to counter these high-altitude, high-speed threats. One of its unique features is its ability to handle extreme temperatures and pressures caused by traveling at hypersonic speeds. When moving this fast, a missile's surface can reach temperatures of thousands of degrees, which can twist its shape and make control difficult. But this latest missile design uses materials that withstand these extreme conditions, keeping it stable. Its heat-resistant design ensures that the interceptor can navigate the intense conditions of hypersonic flight. making it one of the few capable systems in the world able to deal with the challenge. At its core, this hypersonic missile uses advanced guidance technology that combines sensors and artificial intelligence-driven decision-making. This system continuously evaluates the target's path, adapting its course to stay aligned with its target. If the target changes direction, it can instantly recalculate, adjusting its trajectory for maximum accuracy. Its adaptability is important in high-speed interceptions, where even minor errors can lead to a missed target. Its artificial intelligence-driven adjustments help it stay focused on hypersonic missiles, keeping it on track and making sure it successfully intercepts its target. The launch process for SkySonic is just as remarkable. Most missile systems require extensive preparation before launch, with ground crews and a lot of pre-launch checks. This advanced missile's smooth design lets it launch quickly, making sure it can respond fast when needed. It can be launched from multiple platforms, including mobile launchers, making it highly adaptable to various terrains and environments. This flexibility is essential for a system designed to intercept hypersonic threats that could appear anywhere at any time. Another impressive feature of this powerful hypersonic missile is its communication with other defense systems. It is part of a network defense strategy that links Israel's existing missile defense systems. When a hypersonic threat is detected, it can coordinate with radar systems, satellite networks, and ground stations, sharing data in real time. This joint approach ensures that SkySonic has the most accurate information available, increasing the chance of a successful intercept. By integrating with other defense systems, it serves as a final line of defense, ready to respond when other systems may fall short. Aside from the impressive SkySonic, Israel has developed an incredible range of missile defense systems designed to shield its skies. From the Jericho missile to the high-powered Iron Beam laser system and the advanced Arrow interceptors, each defense tool serves a unique purpose. There's also Iron Dome, adding another layer to Israel's strategic defenses. Let's explore how these powerful systems work together to keep the nation safe. The Jericho missile is a powerful part of Israel's defense capabilities, representing decades of innovation and advancement. Designed to carry various types of payloads and reach long distances, these missiles have evolved to meet the demands of modern defense. With each generation named Jericho 1, 2, and 3, these missiles have become faster, more precise, and capable of greater range, making them an essential asset in Israel's strategic arsenal. The Jericho 1 was the first generation, developed in the 1960s with a relatively short range. A single-stage, solid-fuel missile, the Jericho 1 had a range of up to 500 kilometers, allowing Israel to reach key areas within its immediate region. This early version laid the groundwork for later advancements, introducing solid fuel technology that allowed for rapid deployment and simpler storage compared to liquid fuel alternatives. The Jericho 2 brought a major leap in capabilities. Introduced in the 1980s, this two-stage missile extended Israel's reach significantly, achieving ranges of up to 1,500 kilometers. It is capable of carrying larger payloads, including conventional and potentially nuclear warheads, giving the country a much broader range of defense options. Its improved range means it can cover larger areas and respond to threats from farther distances. One of the key advancements with the Jericho 2 is its versatility. Unlike single-stage systems, the two-stage design allowed for improved speed and altitude control, enabling more precise targeting over greater distances. This design set this missile apart, marking Israel's entry into more advanced missile technology. With its larger payload and increased range, it became an essential component of the nation's defense, providing a flexible and powerful tool for strategic protection. While the Jericho 3 represents the pinnacle of Israel's missile development. Entering service in the 2000s, the Jericho 3 is believed to have an impressive range of up to 6,500 kilometers, positioning it as an intercontinental ballistic missile. This third-generation missile can reportedly carry multiple types of warheads, including advanced conventional and nuclear payloads, making it one of the most versatile weapons in Israel's arsenal. Its range allows it to reach targets far beyond the Middle East, establishing a new level of strategic reach. Its three-stage design enables it to travel vast distances with accuracy, making it effective for long-range missions. Its multi-stage propulsion system allows it to ascend to higher altitudes, then re-enter the atmosphere at high speeds, making it harder to detect and intercept. This intercontinental capability is a significant advancement, providing Israel with a missile that can be launched from a secure location and reach far-off targets with precision. Another defining feature of the Jericho 3 is its potential to carry multiple warheads, known as multiple independently targetable reentry vehicles. These warheads allow a single missile to strike multiple targets. This makes it a formidable weapon, capable of overwhelming enemy defenses by delivering several warheads in different locations. The Iron Beam defense system is a game-changer in military technology, using powerful lasers to intercept threats like missiles, rockets, and drones. Unlike traditional defense methods that rely on explosive missiles, it can stop incoming threats with high-energy laser beams. This means it can act fast and efficiently, neutralizing threats almost instantly. It can continue intercepting as long as it has power, making it incredibly reliable for continuous protection. One of the advantages of this defense system is that it's affordable. Traditional missile systems are costly, as each missile launched comes with a high price. Iron Beam, however, operates much more cheaply, which cuts down the cost each time it stops an attack. In places where threats happen often, this lower cost makes it easier to keep up strong defenses without huge expenses. It's a smart way for countries to stay protected without relying on expensive ammunition, making it perfect for areas that need constant defense. Its precision is another outstanding feature. The laser targets only the threat, so nearby areas remain safe from damage. This precise targeting is essential in crowded areas, where protecting civilians is important. Traditional missiles often leave trails of smoke, debris, and noise, which can be risky in populated regions. But this amazing defense system is nearly silent and leaves no visible marks, making it a quieter, safer, and more discreet option for both cities and rural areas where minimizing risks is key. The quick response time of Iron Beam is also a major advantage. Traditional missile systems need a few seconds to prepare and launch, while this system can react instantly, activating its laser as soon as a threat is detected. Its rapid response is perfect for areas vulnerable to sudden attacks. But in certain weather conditions like heavy rain, fog, or dust storms, the laser's effectiveness can decrease because it needs a clear line of sight. Israel's dry climate makes it suitable for Iron Beam, as fewer weather issues mean it can stay highly effective. With future improvements, this defense system's weather limitations are expected to reduce, making it even more reliable in various environments. Aside from intercepting missiles, it is versatile enough to target drones, which are becoming more common in warfare. Drones are often used for surveillance and attacks, and this defense system can neutralize them with the same precision it uses against missiles. This flexibility makes it adaptable to evolving defense needs, as drones continue to be a part of modern conflicts. The system is a great match for current and future threats, providing a flexible and effective solution. Its design is also easy to move and set up. Unlike larger missile systems that require significant preparation, Iron Beam is compact and can be quickly transported and activated. Its setup makes it easy to install wherever needed, offering adaptable defense in critical areas. This flexibility means that it can be positioned wherever threats are likely, adding a layer of security that can adjust to changing needs. Being able to move and set up Iron Beam without any issue ensures that defense can stay ahead of dynamic threats. Countries worldwide are taking notice of Israel's Iron Beam success, sparking interest in similar laser-based defense systems. Traditional systems require regular supplies, while this defense system only needs power, making it simpler to maintain over time. This shift could lead to a new era of defense systems that prioritize efficiency and low operational costs. Its impact may inspire a future where defense technology becomes more sustainable and cost-effective without sacrificing power. The Iron Dome system is designed to intercept and destroy incoming rockets and artillery, as its highly mobile and adaptable defense system has become a technological marvel. Unlike traditional missile defenses that rely on large-scale radar installations and heavy, immovable equipment, this powerful system is agile, precise, and highly efficient. It's built to handle both unpredictable, short-range attacks and larger-scale missile threats, keeping cities and critical locations safe under constant protection. Its true power lies in its rapid response capabilities and its pinpoint accuracy. When a threat is detected, the system is triggered immediately, calculating the incoming missile's speed and direction within seconds. If the threat is likely to hit an inhabited area, It immediately launches a missile interceptor to destroy it mid-air, neutralizing the threat before it reaches its target. The system is also smart enough to ignore missiles that are headed for open fields or non-vital areas, preserving interceptors and lowering operational costs. Its advanced radar and command center work simultaneously to track and evaluate each incoming projectile. The radar scans the skies constantly, feeding real-time data to the command center, where high-speed computers process the information to determine the next move. Once the incoming missile's path is mapped, the system decides whether to launch an interceptor. This entire process takes only seconds, ensuring almost no delay in protecting at-risk areas. Each interceptor missile is fitted with highly advanced guidance technology, allowing it to adjust its course mid-flight to zero in on the target. They can pursue their targets, adapting to sudden changes in the missile's path. This flexibility is important, as it ensures the interceptor can keep up with unpredictable, fast-moving threats, making it effective against short-range rockets. A single Iron Dome battery can protect an area of up to 155 square kilometers, with multiple batteries strategically placed around key areas to form a layered shield over the country. This arrangement creates a wall of protection, with each battery watching over its assigned space and communicating with others to prevent any gaps in coverage. In areas where attacks may be more frequent, several batteries can work together to provide a more concentrated level of defense. This defense system has undergone continuous upgrades, improving its speed, accuracy, and adaptability. Its recent enhancements have made the system even more resilient, capable of intercepting a wider range of missile types, including those with more complex trajectories. As technology advances, so does this defense system, evolving with the needs of modern warfare and adapting to meet new threats. This commitment to constant improvement keeps it ahead of potential adversaries and enhances its reputation as one of the world's most reliable defense systems. Despite its strengths, it's one part of Israel's layered defense strategy, designed to protect against a variety of airborne threats. One of the most impressive aspects of Iron Dome is its resilience in high-volume attack scenarios. During periods of intense conflict, it has demonstrated its ability to intercept hundreds of rockets in rapid succession, keeping up with the pace of attacks without losing effectiveness. Each interceptor missile is designed to be lightweight and responsive, allowing the system to deploy them quickly in response to multiple, simultaneous threats. Israel's Arrow 3 missile defense system is a powerful shield against some of the world's most dangerous missiles. It's not like ordinary missile defenses that intercept threats closer to the ground. It is designed to target and destroy ballistic missiles high up in space. This special feature makes it one of the few systems able to intercept missiles carrying nuclear or chemical weapons at a safe distance, far from people or cities. Instead of using explosives to destroy an incoming missile, it relies on hit-to-kill technology. This means it collides directly with the threat, using force alone to break it apart. This method is clean and effective, destroying the missile without scattering harmful debris or materials over populated areas. One of the most remarkable aspects of this powerful missile is its ability to reach targets in space. While most defense systems work within the sky, this missile system can intercept threats as soon as it is launched, catching the target in the early stages of flight. By intercepting missiles while they're still in space, Arrow 3 avoids the situations that happen when missiles enter the atmosphere, like rapid speed and extreme heat, which make them hard to stop. This special ability puts this advanced system in a small, top group of missile defense systems worldwide. Its precision tracking and targeting are also extraordinary. Using advanced radar, it can detect an incoming missile from hundreds of miles away, calculating an interception point with amazing accuracy. The system tracks the missile's path, updating in real time if the target shifts or speeds up, ensuring that it stays locked on until it makes a successful intercept. Even at the high speeds and extreme distances of ballistic missiles, it remains on target. Another impressive part of this hypersonic missile is its two-stage launch design. The first stage moves the interceptor into space, while the second stage takes over and guides it directly to the target. This two-step process gives it greater range and flexibility to adjust its path if the target's direction changes mid-flight. It plays a crucial role in Israel's multi-layered defense system. While the Iron Dome handles short-range rockets and the Iron Beam takes out drones and smaller threats, Arrow 3 is built for long-range ballistic missiles that approach from afar. Each system works together, focusing on different types of threats to create a strong, layered shield. From close-range rockets to high-altitude missiles, Israel's defenses are designed to handle it all. Arrow 3 has already shown its capabilities in multiple tests, successfully intercepting fake threats in space. These tests aren't just for practice. They are to prove that the system works in real-world situations, and it has passed with top marks. The success of these trials has only strengthened trust in this defense system's ability to protect against advanced missile threats, showing that it's ready for action. What sets SkySonic apart from other interceptors is its proactive approach. Instead of reacting to a threat, it anticipates and intercepts it before it can get close. By accurately predicting the path of a hypersonic missile, it ensures the target is destroyed far from its intended destination. This early intercept strategy prevents damage to sensitive areas and reduces the risk of collateral damage. Unlike traditional defenses, which rely on brute force, SkySonic's approach is precise, calculated, and highly efficient. The course of the Israel-Hamas war is about to change. As this conflict intensifies, the U.S. has sprung into action and deployed the world's most powerful aircraft carrier to the Middle East. But this colossal vessel won't be alone. It will be accompanied by a formidable group and a mysterious aircraft that has everyone talking. What could this unknown aircraft mean for the future of the conflict? What makes it stand out from other aircraft? Join us as we unveil the mysterious UFO aircraft on the United States Navy aircraft carrier in the Mediterranean Sea. In a recent development, Secretary of Defense Lloyd Austin has ordered the USS Gerald R. Ford carrier strike group to move to the eastern Mediterranean Sea in response to the recent attacks on Israel by Hamas. The carrier strike group has been stationed in the Mediterranean since June, initially as a show of strength due to Russia's invasion of Ukraine. This powerful group includes the aircraft carrier USS Gerald R. Ford, the guided missile cruiser USS Normandy, and several Arleigh Burke-class destroyers like the USS Thomas Hudner, USS Ramage, USS Carney, and USS Roosevelt. Before the recent move, the strike group was operating near Italy. Now, with the new orders, they are heading closer to Israel. In addition to repositioning the strike group, Austin also announced plans to send more U.S. fighter planes to the region, including F-35 Joint Strike Fighters, F-15, F-16s, and A-10 tactical aircraft, showing how seriously the United States is taking the situation. Austin's actions came after he spoke with President Joe Biden about how the U.S. should respond to the Hamas attack on Israel. He said these moves are meant to strengthen the United States military presence and show strong support for Israel. However, on Saturday, Hamas surprised Israel with an attack from the Gaza Strip, catching the Israel Defense Forces off guard in southern Israel. According to reports, there are hostages and prisoners of war, and the exact number of casualties among Israeli soldiers is still unknown. Hamas, a group considered a foreign terrorist organization by the U.S., governs Gaza, which Israel occupies. So far, more than 600 Israelis and 400 Palestinians have been harmed, according to Israeli newspaper Haaretz. Quite recently, Austin spoke with Israeli Minister of Defense Yoav Gallant to express United States support for Israel and to get updates on Israel's actions to restore security after the attack. Austin emphasized that these U.S. military actions are meant to reinforce the region and help Israel defend itself, showing the U.S.'s firm commitment to helping its ally. The USS Gerald Ford would not be going alone. It would be equipped with one of the most dangerous and advanced drones in the world, the X-47 drone. What is its capability and what makes it different from other drones? The X-47 drone started with the Joint Unmanned Combat Air Systems program in the early 2000s. This was a joint effort by the U.S. Navy and Air Force to build an unmanned fighter. The program was canceled in 2006, but the Navy believed in the idea and brought it back under a new program called UCAS-D. This is where the X-47B took shape, thanks to Northrop Grumman. This new drone was designed to be a tailless, jet-powered fighter that could fly by itself, refuel in the air, and handle sea conditions. Since the X-47B had to deal with saltwater, rough sea landings, and complex carrier systems, the project cost a lot. By 2012, the total cost had risen to around $813 million. But the Navy kept funding the project because they knew how important the X-47 would be. This aircraft could fly into dangerous areas, identify targets, and even launch attacks with its two weapon bays that can hold 4,500 pounds of bombs. This drone was fast, powerful, and smart. It had a near supersonic speed, could fly as high as 42,000 feet, and had a range of 2,400 miles. The X-47B performed incredibly well in tests. It launched from aircraft carriers, landed safely, refueled in midair, and operated in difficult environments. It also integrated perfectly with the Navy's carriers. In 2012, it began testing on the USS Harry S. Truman and passed with flying colors, showing it could work with the flight deck, hangars, and communication systems. This success means the USS Gerald Ford is even more powerful with the X-47B on board. Once the X-47B is developed into a more powerful version, the X-47C, which will carry up to 10,000 pounds of bombs, the USS Gerald Ford will be even stronger. But even now, it's one of the greatest forces in the world, and here's why. The USS Gerald Ford is the leader of the U.S. aircraft carrier fleet. The United States owns about 25% of the world's aircraft carriers, and their total deck space is more than double all other nations combined. The USS Gerald Ford is powered by 2 nuclear reactors, which means it can run for 25 years without needing to refuel. This gives it a huge advantage, allowing it to travel around the world without stopping. With a top speed of around 30 knots, the carrier can reach any country quickly, whether it is to support allies or strike enemies. The USS Gerald Ford is also incredibly smart. It uses artificial intelligence and unmanned vehicles, like the X-47, to carry out missions. With fewer crew members needed, the ship has more space for advanced systems and weapons. This also gives the 4,500 crew members a better quality of life, with ergonomic workspaces and gym facilities. The carrier is equipped with the most advanced sensors and radars. Its radar system, the AN/SPY-3, is the most advanced of its kind, capable of handling the surveillance, air traffic control, missile communications, and target detection from miles away. This technology ensures the USS Gerald Ford remains a step ahead of any threat. The carrier can hold up to 70-30 fighter jets and unmanned aerial vehicles, including the Navy's F-35C Lightning II, one of the most advanced jets in the world. The F-35C can do it all, from vertical takeoff and landing to close air support. It's a versatile and powerful fighter, making it the Navy's top choice until the next generation F/AXX fighter is ready. To launch and recover its aircraft, the USS Gerald Ford relies on cutting-edge electromagnetic systems. Its electromagnetic aircraft launch system, also known as EMAL, propels the aircraft into the sky quickly and safely, while the advanced arresting gear ensures smooth landings. These powerful systems outperform older steam-based technology, allowing the carrier to launch more aircraft in less time. With 11 elevators to swiftly move planes and weapons, the Ford is always ready for action. At the same time, Israel's air power took a leap forward with the acquisition of the F-35 Lightning II. In a deal with Lockheed Martin, Israel secured the F-35 Ayadir for its Air Force, and by December 2015, the first jets were operational. Just months later, in May 2018, Israel made history as the first nation to use the F-35 in combat, with the jets playing a key role in the Israel-Hamas conflict. The F-35I has since become a crucial asset, stationed at Nevatim Air Base and serving in 3 elite squadrons. The history of Israel's involvement with the F-35 began in 2003, when Israel signed a $20 million agreement to join the aircraft's development as a security cooperation participant. The Israeli Air Force identified the F-35 as crucial to its future plans and aimed to buy over 100 jets, replacing its aging F-16s. Israel rejoined the F-35 development program in 2003 after resolving tensions with the U.S. over a Chinese arms deal. Throughout the 2010s, Israel worked to customize its F-35s to fit its unique needs. Israeli companies developed smaller missiles, while the Defense Ministry pushed for more local involvement in the production and maintenance of the jets. Israel's defense minister at the time, Ehud Barak, advocated for these enhancements to maintain Israel's technological advantage in the Middle East. Despite criticism from Israeli contractors and high costs, The purchase of 20 F-35s was finalized in 2010, with American military aid covering much of the cost. The total price, including training and spare parts, was about $96 million per plane. Incorporating Israeli-made systems, particularly in radar, electronic warfare, and communications, was a top priority. However, the first batch of F-35s included only limited Israeli systems, with a promise for more customization in future purchases. Lockheed Martin agreed to buy parts from Israeli companies, boosting Israel's defense industry. Despite concerns about the cost and benefits, Israel's commitment to maintaining military superiority pushed the F-35 deal forward. This advanced jet is seen as crucial for Israel's defense strategy, offering cutting-edge capabilities that ensure its technological advantage in the region. The F-35s are specially adapted to meet Israel's unique defense needs, and plans for additional purchases are being considered to further strengthen its air force. While the F-35 represents the future of Israeli air power, the country's aviation legacy is rooted in earlier innovations, like the Israel aircraft industry's Kafer, meaning lion cub in Hebrew. The Kafer is a versatile all-weather combat aircraft based on the French Dassault Mirage 5, but with Israeli-made avionics and a locally produced General Electric J79 turbojet engine. The Kafer's story began when Israel needed to improve the Dassault Mirage 3C to better suit its air force. The Mirage 3CJ, known for its delta-shaped wings, was the first plane in Israel's fleet capable of flying twice the speed of sound. It was vital to Israel's air force during the 1960s, until newer planes like the A4 Skyhawk and F4 Phantom II arrived. Although the Mirage 3CJ was great in air combat, its short range made it less effective for ground attacks. In the mid-1960s, Israel asked Dassault Aviation to create a ground attack version of the Mirage 3, which became the Mirage 5. This version had its advanced electronics removed to allow more fuel storage, reducing maintenance costs too. By 1968, Dassault had completed 50 Mirage 5Js for Israel, but after a French arms embargo in 1967, Israel couldn't receive the jets. Determined, Israel made its own version of the Mirage 5, called the Nesher. They managed to get the design plans through Israeli intelligence efforts, allowing them to build their own aircraft. The Kafer program started when Israel wanted to create a better version of the IAI Nesher, which was already in production. After General de Gaulle stopped selling arms to Israel, the Israeli Air Force worried that they might lose their edge against enemies who were getting more advanced Soviet planes. The Mirage was the IAF's most advanced aircraft, but many were lost after the Six-Day War. So Israel decided to build their own planes to avoid the arms embargo. They even used espionage to gather technical information and blueprints from other countries using Mirages. Initially, two engines were tested, the General Electric J79 turbojet and the Rolls-Royce Spey turbofan. Ultimately, the J79 was chosen because it was also used in the F4 Phantom II, which Israel began acquiring from the US in 1969. The J79 outperformed the original French Ataro 9 engine, providing strong thrust for better performance. To fit the J79 engine into the Mirage 3's design and provide better cooling, the aircraft's rear was slightly shortened and widened, and the air intakes were enlarged. A large air inlet was added near the vertical stabilizer for extra cooling. The engine was protected by a titanium heat shield. A two-seat Mirage 3BJ with the J79 engine first flew in September 1970, followed by a re-engineered Nesher in September 1971. An improved version, named Rayam B, took its first flight in June 1973. It featured a redesigned cockpit, stronger landing gear, and many Israeli-made avionics, with fuel capacity increased to 713 US gallons. Though rumors suggest that some original Mirage 3Cs were re-engineered with the J79 and dubbed Barak, flying during the 1973 Yom Kippur War, no solid evidence has confirmed the existence of these modified planes. While the Mirage stories remain uncertain, the F-15 Ra'am fighters are a proven and a very important asset in the Israeli Air Force. Although the newer F-35 tends to steal the spotlight, the F-15I plays a very important role with its longer range, making it ideal for long-distance strikes and maintaining air superiority. The Ra'am, developed from the American F-15 Eagle, is loaded with cutting-edge technology, weapons, and electronic warfare systems. These planes have played key roles in conflicts in Lebanon, Syria, and Gaza, and they can strike deep into Iranian territory, supporting Israel's defense strategies. Even though the F-35Y is recognized as Israel's top fighter, the F-15Y should not be underestimated. In fact, the Rayam fighters have a greater range than the F-35s and F-16s, which is crucial as the conflict with Hamas continues to unfold. The IAF's aerial power is essential for Israel's security, and the F-15Y Rayam is a significant part of this effort. The F-15 Eagle first took to the skies almost 40 years ago, designed to replace the aging F-4 Phantom II. In the early 1980s, the Eagle stood out as the U.S. Air Force's top pick for a new tactical fighter, thanks to its cutting-edge design, lower costs, and ability to evolve with future technology. Following the 1991 Gulf War, Israel's leaders saw the need for long-range aircraft to neutralize threats. Iraq's Scud missile attacks had revealed gaps in Israel's air defenses, making long-range strike capability critical for the country. To address this, the Israeli Air Force decided to purchase 25 of this jet in the mid-1990s. Israel was already familiar with the F-15, having flown it since 1978 during operations in Lebanon, where it performed impressively against Syria's MiG jets. The Rayam's advanced radar systems and formidable firepower make it a powerful force in the skies, capable of handling a variety of missions with precision. Its ability to carry up to 18,000 pounds of weapons and fuel, along with its twin engines that can push it past Mach 2, solidify its role as a key asset for the Israeli Air Force. Similarly, the McDonnell Douglas F-4 Phantom II, an American jet fighter, earned a reputation for versatility and power. Initially built for the U.S. Navy, this twin-engine aircraft quickly became a multi-role supersonic interceptor and fighter bomber. During the Vietnam War, the F-4 played a very important role, serving as the main air superiority fighter for U.S. forces. It also excelled in ground attacks and aerial reconnaissance as the conflict progressed. Notably, all 5 American servicemen during this war did so while flying F-4s. The Phantom remained a key part of U.S. military power throughout the 1960s and 1980s, eventually being replaced by modern jets like the F-15 Eagle and F-16 Fighting Falcon. Even after the Vietnam War, this aircraft continued to serve in various roles, including reconnaissance and suppressing enemy air defenses during the 1991 Gulf War, retiring from combat service in 1996. It was also the only aircraft flown by both the U.S. Air Force Thunderbirds and the U.S. Navy Blue Angels. Beyond the United States, the F-4 was used by the armed forces of 11 other nations. Israeli Phantoms fought in several conflicts against Arab nations, and Iran used its fleet during the Iran-Iraq War. This leads to the question, what makes this aircraft special? The F-4 Phantom is a 2-seat fighter bomber built for the U.S. Navy, designed to defend the fleet from enemy aircraft. It features cutting-edge technology like advanced radar and uses a lot of titanium in its structure. Despite its large size and weight of over 60,000 pounds, the F-4 can reach speeds over Mach 2.23 and climb quickly at more than 41,000 feet per minute. It has 9 hardpoints that can carry up to 18,650 pounds of weapons, including missiles and bombs. Originally, it didn't have an internal gun, which was common for jets of its time. This design became the blueprint for future fighters, focusing on long-range missions and heavy payloads, particularly for daytime air combat. For the pilots that graced the cockpits of the F-4, speed is life was their motto, as the Phantom's rapid acceleration gave them control in dogfights. While it had powerful engines, its bulky design made sharp turns difficult, allowing Soviet rivals to outmaneuver it. Despite this, the F-4 remained responsive, and in 1972, the F-4E model's upgraded design improved its handling in tight maneuvers, even if it slightly reduced its top speed. The F-4 was powered by the J-79 engine, which responded quickly when pilots pushed the throttle. There was a famous incident where a pilot missed the landing gear on an aircraft carrier, but quickly regained control by slamming the throttle to full power, allowing him to take off again. However, the J-79 engine produced a lot of black smoke, making it easier for enemies to spot. Many pilots felt that the lack of an internal gun was a major mistake. They believed having a gun would be more reliable than missiles, which were often unreliable during combat. At first, there was a belief that turning dogfights weren't possible at high speeds, so pilots weren't trained in aerial maneuvers. However, in practice, fights often slowed down as pilots tried to position themselves behind enemies. The F-4C eventually carried external gun pods with a 20-millimeter cannon, but these were often inaccurate and problematic. The problem was finally solved with the F-4E, which included an internal cannon for better performance in air combat. These powerful fighter jets, combined with United States involvement, could be the key to bringing an end to this long-standing conflict and finally restoring peace between the two regions. The U.S. military's top-secret UFO laser jet is either the most significant leap in aerospace history or the most remarkable government cover-up ever. Reports suggest this advanced craft may possess extraterrestrial-inspired technology, complete with energy-based weapons and unmatched maneuverability. Could this breakthrough revolutionize air combat as we know it? And if such technology exists, what else is being hidden? Join us as we explore the mysteries behind this rumored jet, dissect the facts, and understand why the U.S. top-secret UFO laser jet is finally entering production. There has been increased debate on UFOs in recent times, especially with studies by NASA and the Pentagon now calling them unidentified anomalous phenomena, also known as UAP. Both organizations stress that while many sightings can be explained by natural or man-made activities, the others remain unexplained because either there is inadequate quality data. In 23 years, NASA invited the public to scientific scrutiny of such accounts. However, no physical evidence of extraterrestrial technology, including the alleged UFO laser jet and the like, has been unearthed. However, an array of more precise, structured data is accumulated to improve the situation in the airspace and meet the goals of national security. Unlike before, there has been a marked increase in the public's interest in UAPs due to accounts from the U.S. government and its military. However, they appear to have made general news without offering concrete evidence of aliens' technology. The Pentagon UAP report of 2021 pointed out more than 140 cases. Several of them concerned unidentified objects flying in manners that could not be explained. The majority of incidences could be due to conventional technology, including drones, atmospheric effects, or even another country's weapon system. Of the 144 submitted descriptions of UAPs, reports from the U.S. Department of Defense and intelligence agencies admit that limited data and techniques have precluded them from detecting most of these objects. Still, what may be expected regarding the time and features of the jet's entry into production, its market potential, and potential engineering breakthroughs that it may imply? At present, there are no authentic sources or details regarding the fabrications about a secret UFO laser jet tied to the U.S. However, the initiation of theories relating to elevated airborne technology often stems from speculation or false reports rather than records of military integrity. However, suppose such a project were to exist. In that case, the overall purpose, as well as the capacities of future projects, may correspond with improving aerial combat surveillance capabilities similar to sophisticated existing U.S. military aircraft. Arguably, one of the set goals of a hypothetical UFO laser jet is to have high responsiveness. Built to be stealthy and perform quick acrobatics, this airplane may pose a higher degree of threat than these well-known models of airplanes, the F-16 Fighting Falcon or the F-35 Lightning II. Each of these aircraft flies with good maneuverability and an avionics system. Still, a future jet may use superior technologies that will allow it to outturn its opponents and rapidly change its maneuvers to adapt to the new battle tactics. A new facet of this sophisticated jet may include integrating laser weapon systems. Suits might be used for pinpointing, jamming, or shooting down enemy systems or incoming missiles with great accuracy. This capability would be innovative from the current conventional ordnance employed in presently used aircraft. For example, the FA-18 Super Hornet, which uses bombs and missiles. The application of laser technology into another imaginary aircraft called the UFO laser jet is a step up towards improved combat capability over the existing weapons. Stealth technology is also expected to be used in the creation of this jet. Current systems include the B-2 Spirit and the F-22 Raptor, which rely on unique facets that help in low observability to radar. Thus, the UFO laser jet would have to expand on this tradition of stealth, applying additional extensions to penetrate as deep as it needs to into the enemy airspace, perform its mission, and get out unscathed. Apart from combat purposes, the jet can be designed for reconnaissance missions similar to the Northrop Grumman RQ-4 Global Hawk, which serves high-altitude, long-endurance surveillance. The hypothetical plane would be equipped with new-age sensors and reconnaissance systems, which would allow it to gather intelligence from hostile territories to support extraordinary decision-makers. This capability would improve the state of awareness and planning and executing tactics in a given area. In addition to all these features, the aircraft might take a fully automated control or remote control, minimizing the risk a human pilot might be exposed to in volatile zones. Unmanned operations would offer more strategic planning and execution of missions like the MQ-9 Reaper drone, which takes time to take direct combatant orders. This feature would make it possible to achieve military tasks without risking the lives of people. With all these features in place, what are the national security implications of this development, particularly in terms of its effects on defense strategies, intelligence operations, international relations, and the potential for altering the balance of power between nations in an increasingly complex global landscape? One of the primary concerns would be establishing technological superiority over potential adversaries. If the U.S. were to deploy capabilities like a laser jet, it could create a significant advantage in military operations, enhancing deterrence and rapid response capabilities in conflict scenarios. This situation mirrors the impact of the stealth technology exemplified by the F-22 Raptor, which has established air dominance due to its ability to evade detection. However, such superiority could provoke rival nations to expedite their military research and development efforts, potentially igniting an arms race in advanced technologies. This is reminiscent of the Cold War era when both superpowers sought to outdo each other in nuclear capabilities. The allure of cutting-edge technologies often attracts espionage efforts from foreign adversaries eager to gain insights or steal intellectual property. The advanced nature of technologies like a hypothetical laser jet would likely heighten the risk of sophisticated cyber attacks or espionage activities targeting sensitive military research. This concern is evident in ongoing issues faced by the U.S. military regarding cybersecurity vulnerabilities, as seen in high-profile breaches involving defense contractors and government agencies. The challenge of safeguarding critical information underscores the necessity of robust security measures as the U.S. continues to innovate. Additionally, the introduction of new technologies can disrupt existing power balances and lead to strategic instability. For instance, if the UFO laser jet were perceived as a transformative force in warfare, adversaries might rush to develop countermeasures, resulting in a cycle of escalation. This phenomenon is similar to the historical development of missile defense systems, which have prompted reactions from nations like Russia and China, leading to heightened tensions and complicated diplomatic relations. The dynamic nature of technological advancement in warfare necessitates careful consideration of its impact on global stability. Operational security challenges would also become more pronounced with the introduction of advanced military technologies. As new systems are developed, maintaining operational security to prevent unauthorized access and exposure becomes increasingly complex. The potential for adversaries to exploit vulnerabilities in these systems could undermine their effectiveness in combat. This concern parallels the ongoing struggles faced by the U.S. military to secure its networks against cyber threats, highlighting the critical importance of safeguarding advanced systems. Moreover, the possession of advanced military capabilities could reshape international alliances and partnerships. Countries that develop superior technologies might emerge as key players in global defense, altering existing alliances. Nations may seek to align themselves with technologically advanced allies for security assurances, a trend seen during the Cold War when alliances were often formed based on military capabilities. This shift in international relations could influence collective defense agreements and the dynamics of global security cooperation. The ethical considerations surrounding the development and potential use of advanced military technologies warrant careful examination. The implications of employing systems like laser weapons could lead to intense debates over rules of engagement, collateral damage, and the moral responsibilities of using such capabilities in warfare. This concern resonates with broader discussions in military ethics, particularly regarding autonomous weapons and advanced targeting systems. These discussions emphasize the need for clear guidelines and accountability in the application of new technologies. How can the U.S. continue to control this potent technology, given that the rise of international competition poses a severe threat to its dominance? Is the country's safety and security threatened by the use of this potent technology? Holding control over sophisticated equipment that is useful in operations and has military value is a crucial factor for any government, particularly the U.S. government. To protect information containing such technologies, the U.S. Department of Defense, also known as DoD, has traditionally used a layered approach that commences with classified research and development. Some of the most advanced military programs are shrouded in high levels of confidentiality and secrecy, therefore ensuring that the DoD conceals pertinent data on capability or designs. This same general idea applies to such advancements as stealth technologies used in such planes as the B-2 Spirit bomber, where secrecy is all that counts to fend off adversaries. Access to sensitive technologies is equally protected by strict security clearances. Such clearances are mandatory for employees who are engaged in secret military projects, so only those who are privileged with such information should be in a position to access sensitive information. It is similar to the action taken in other cases, such as organizational management of nuclear weapons, where limiting controls ensure that only authorized persons gain access to the gun and that its access cannot be given to unauthorized persons, leading to occurrences of security invasion. The United States also depends significantly on the defense industrial base and private companies to produce more sophisticated systems for use in the military. This collaboration entails monitoring through contracts and regulations to safeguard information at different stages of production. Similar facts can be observed in projects to create innovative products, such as the F-35 Lightning II, which involves several companies that work on different parts of the aircraft and implement security measures to protect information. Effective control of export-sensitive technologies is thus attributed to export controls. The federal government of the United States has put in place its trade control regulations, including the International Traffic in Arms Regulations, also known as ITAR, and the Export Administration Regulations EAR, to regulate the export of certain technologies to foreign individuals or companies. This was similar to rigorous standards governing the sale of military equipment to friends and allies, to avoid funds getting into the wrong hands due to the transfer of sensitive technology. Security is another input that solves the objective of protecting advanced military technologies. The American military and the manufacturers of its defense resources spend a lot of money on cybersecurity to protect critical information and servers from malicious cyber attacks. This dedication of resources to cybersecurity is on par with the measures being made to safeguard other vital systems like banking and energy, where the effects of a break-in can extend exponentially. Moreover, the U.S. conducts research in cooperation with other friendly countries. It ensures the protection of obtained data concerning the permitted use of these findings. This approach is practical in knowledge sharing while managing key competencies, because the key capabilities are never exposed. The same is found in multinational military maneuvers, where information sharing occurs. Yet there are measures in place to guard intelligence. Ultimately, the DoD, other federal agencies, and other regulatory bodies conduct periodic overhauls and compliance assessments to guarantee compliance with security measures and shield innovation from potential leaks or tampering. This practice is observed in a range of programs across military platforms. Not least, the following are examples of managing logistics and supply chains. Strict compliance with safety benchmarks is required to protect sensitive information from leakage and the overall integrity of organizational operations. With all these, will this technology be shared with allies? And if so, how will the process be managed in terms of international agreements and security clearances, while also considering the broader implications for joint defense initiatives? Suppose the United States has a top-secret UFO laser jet. In that case, it will have to consider many factors, whether or not to share this technology with its allied states. Traditionally, some nations have provided their closest friends and allies, especially those within a mutual security pact, with sophisticated equipment. For example, the F-35 Lightning, a fifth-generation stealth fighter, is being used as a show of force among a limited number of countries, including the UK, Israel, and Japan. However, if a firm is developing highly speculative or next-generation systems, such as a laser jet, the U.S. could be more reluctant. The competitive edge that results from such a technology means that its distribution would have to be well-guarded and restricted to probably the most significant and reliable partners. The U.S. has never chosen to provide its best-equipped defense technologies with any other country, and this has been with good reason and effect. Some are topical, like the F-35 or Patriot missiles, in order to bolster the defense of the member states in the alliance, while others, like the stealth B-2 Spirit aircraft, are kept exclusively for American usage. In this manner, this selective sharing mirrors the U.S. military's policy of asymmetrical warfare, where possible gains holding the advantages of any given plan are held against the need to maintain alliances. Suppose the U.S. were to develop a laser jet. In that case, it is likely to emulate this trend and specify which of its allies will be granted the technology and under what conditions while maintaining the security of this country. But most importantly, what kind of role shift could this emerging technological capability play regarding the following variables related to future warfare? The existence of such machinery, as assumed, might considerably shift the future of warfare in different ways, as outlined below. As one of the most conspicuous impacts, asymmetric warfare may result. If the U.S. builds capabilities that are significantly higher than those of its enemies, it would become imperative for conflict dynamics. This situation resembles the stealth technology seen in bicameral aircraft such as the F-22 Raptor. The stealth option means surprise and better positioning. These key factors change the approaches to warfare established by the F-22. If invented, the laser jet could afford a similar value proposition, transforming military conflict and possibly making traditional strategies and approaches ineffective. The adoption of newer technologies would probably require a rethink of how to wage war. For instance, if the UFO laser jet had only laser weapon systems on board, then the force transformations might be moved from kinetic weapons to energy weapons that have target accuracy and a very low probability of collateral damage. This evolution would mean a profound change to military forces practicing and engaging in specific types and ways of battle, as we saw with the introduction of drones into warfare. The UAVs have revolutionized reconnaissance and strike missions, making them more effective, efficient, and accurate, thus showing how new technology can change the operational milieu. Afterward, the inclusion of such sophisticated systems would probably improve the cybersecurity prowess. Suppose the laser jet was a hypothetical technology. In that case, it may include many cyber elements, which would make its operations real-time data and decision capability, thus increasing its operation effectiveness. At the same time, these also throw up potential issues. An enemy can always attack and disable these systems that are otherwise enhancing a nation's strength. This situation is similar to today's cyber warfare, where disruptions in the military networks can show how adversaries take advantage of the weakness. This advancement of military technologies usually leads to the development of race between the countries. In the case where the U.S. decided to launch a laser jet, it would force other nations to speed up their technology, thus resulting in more profound military developments and therefore increased global tensions. This is consistent with the Cold War, when innovation in nuclear weapon technology led to the development of arms races among superpowers. The drive for the newest, best technology may result in a similar situation today as nations seek new combat functions. In addition, owning such modern technologies as a laser jet can help enhance deterrence strategies. The state might refrain from confrontation with such a power, as it can see the danger of losing in confrontation with a country with superior potential proved by nuclear capabilities. It may increase the chances of the risk discouraging aggression or preventing the heightening of intensity. This seems to be related to the balance of international politics that has marked relationships between nations, mainly during moments of innovations in technology in relation to military formations. The development of such complex weapon systems in different states could revolutionize global politics through the formation of cooperation through technological capacities. Although no country would want to rely on an ally's ability to provide it with security from the said technology, military alliances may be sought based on armed capabilities, like how defense technology coalitions have been sought in the past. This situation, in turn, can result in a shifting of geopolitical strategies that may bring about a shift in alliances in terms of ICT development. In conclusion, while the concept of a UFO laser jet remains hypothetical, its potential development highlights the broader challenges that come with advancing military technology. It would undoubtedly enhance U.S. military capabilities, but it would also create new security, strategic, and ethical dilemmas that would need to be carefully studied and applied. The global arms race, operational security concerns, shifting alliances, and ethical implications highlight the complexity of integrating such groundbreaking innovations into modern warfare. As history has shown, the pursuit of technological superiority in the military domain can have both stabilizing and destabilizing effects on global security, and careful consideration is essential to ensure these technologies are used responsibly. Thanks for watching. While you are still here, click on the link on your screen to check out another of our videos. See you there.